Buenos días, pues vamos a seguir hoy jueves con este segundo día de las jornadas sobre seguridad informática enmarcadas dentro de la Cyberweek en Girona. Para empezar el día nos acompaña desde Levenpads Santiago Hernández, viene de Telefónica de Levenpads y nos va a hablar sobre malware análisis, en concreto sobre ransomware, ¿entiendo? No exactamente. Bueno, efectivamente. Pues dejemos que nos lo explique él y empezamos este segundo día. Muchas gracias por venir.
Okay, so I will try to speak in English for the conference, so sorry if my English is not the best, but okay. So thank you everybody for coming to my talk. My name is Santiago Hernández. I'm currently working at 11 Paths as a security researcher, and today I'm going to talk about malware analysis. I'm going to talk about the difference between traditional malware and modern malware. And after that, I'm going to explain how easy it is today to create your own malware. And I'm going to do a demonstration about how can we create a malware from some existing pieces of code and some security issues that are public in internet. So, first of all, I'm going to start talking about how was traditional malware. Traditional malware normally work as I have put here in the slide. So some years ago, when a malware was released, normally that malware starts by scanning a network. So it starts scanning the network, searching for example, some ports that are open, for some services that were running in that port, and after that, it will search for the versions of that services. So it can search after that if that services are vulnerable. So once that malware have searched for that services, it will find some exploits or some public exploits that it can exploit that services, so the malware can have access to the machine. Once the malware have access to the machine, by exploiting that vulnerability, it will start installing itself somewhere in the network, maybe in some machine or maybe in some server, wherever. And once it is installed in one machine, it will start spreading throughout all the network. So it will start looking in the network from other nodes to install in that other nodes. So modern malware have more or less some similar steps. In general, that steps are mostly the same, but some of that general steps, if you look it in deep, it have changed a lot and are very different. I have put there 4 main steps that mostly all modern malware perform. So first of all, it will look for an entry vector. The entry vector is just the way that the malware we use to enter in the network or to enter in a machine. This is one of the important points because it's one of the things that more have changed between the traditional malware and the modern malware. After that, it will probably use an exploit for escalation privilege and have some more privilege so they can perform some actions. After it have used an exploit for escalation privilege, it will try to get some persistence. And after the persistence, he will establish a back channel so the attacker can start, for example, exfiltrating data from a network or from a machine, or it can use that back channel, for example, for delivering another program or another exploit or a ransomware or whatever. So I will start to explain all these steps one by one. And after that, we will perform all these steps in practice. So first of all, the entry vector. So how has changed this step between traditional malware and modern malware? So how I explained before, traditional malware tried to start by scanning, for example, a network, by searching for open ports, by searching for services that were running in that open port, and the version of that services, trying to exploit that services. But nowadays, that is very difficult, and almost any malware do that. Why? Because companies, for example, nowadays have a lot of security technologies in the perimeter of their network. And if you start, for example, by scanning some IP public address or something like that, you will not find any service or any port open that normally you can break or you can use to get access to the network. So that direct way for accessing to a network have changed for some indirect ways. So why that change? Some of the things that most have changed also is the profile of the attackers. So the attackers in traditional malwares can be, for example, a guy that only wants to release a worm in the internet or to some public IPs that maybe he only wants to extract from some data, or maybe is doing it just for fun. Today, that have changed a lot. Today, all big malwares are released by organizations that will use that for get money. So, they, first of all, are going to set up a particular target, and we will attack that target. That target can be, for example, a person, or can be a company, or can be a set of companies, or can be a country, but they will have very clear their target. Once they have their target, they will research that target. So they will know what are the weak points for that entry point on that target. So how are they going to enter? They are not going to enter through the firewall, through the IPs, through the IDs, and all that security technologies, because it is very difficult to do that. They are going to enter in an indirect way. So they're probably going to start to make some target or spear phishing that is basically research a person or research a set of persons and try to make some phishing. They are going to, for example, use your bad Wi-Fi configuration for getting to the network, and once they are into the network, they are going to release some exploit or something like that. They are going to use your access control to your intranet, or, for example, one of the things that a lot of companies don't have in account is that nowadays all the applications have evolved. So the last 10 years, the phishing, for example, was performed by email. And that was the first entry point for phishing, the email. And of course, nowadays, all the companies protect their email for phishing and all that things. But the real situation is that nowadays, there are a lot more apps that are being used in the companies, like, for example, Dropbox, Skype, that are currently used for split phishing and other things. For example, for split exploits, and that are very difficult to control, and the majority of the companies don't control. So once we have that entry point very clear, what they are going to do is just release an exploit and send that exploit to the user, or maybe they can get into the network because the Wi-Fi configuration is not good, or whatever. Once they are in, they are going to release the exploit. In the worst case, that exploit will be a 0-day, that nobody knows about it, and that will perform an escalation privilege. They will obtain the better privilege, and they will start moving through their network, opening a back channel or whatever. But what is the real problem here? When a 0-day is released and an exploit becomes public, there pass a few months between that exploit becomes public, the code of that exploit, and for example, the security firms start to release some things and some patches for that exploit. And it pass some more days between that patches are public and the companies start updating their servers and their machines. So in that time that passed through that, other people around the world start using that public exploits, and they don't know how they have to code that exploit or what vulnerability are that exploit exploiting. They don't know nothing about it. They just take the code and use that code in its own malware. So that's a big problem, because in that month that the exploit become public and the exploit become patched and the companies patch that exploit, there are thousands of computers in the world that are vulnerable. So the third step that I have put here is persistence. So once the exploit have make a privilege escalation, they will try to make some persistence. And the persistence is something that it's been already studied a lot. So you can make, for example, some persistence by inserting a payload in the Windows registry keys. You can, for example, hijack a DLL. You can insert some code in the kernel. You can do a lot of things here, and this is widely known. The last thing that the malware will do is probably they will open a back channel. And the back channel will be just, for example, a remote TCP connection, or will be other type of reverse connection. This back channel will be, for example, if it's a data breach, it will be used for extract data. If it's a ransomware attack, it can be used for opening that back channel, and use the back channel for release the ransomware that will cipher the disk or something like that. The problem here is that you can detect, for example, some reverse connections that are strange, but sometimes attackers use reverse connections that they look totally legitimate. So it's very difficult to detect that. Other thing that is commonly used for extracting data, for example, is steganography. What happens with this? This is something that is very difficult to detect, because you can mostly hide data in all parts. For example, in 11 parts last year, we use latch for exfiltrating data. So latch is can be in two stages. For example, that can be in a position that is closed, that represents that we suppose that represents a 0, and it can be open, and we suppose that represents a 1. So, for example, if we have fake latch in a machine, just by its state of open or close, we can exchange data with other machine, just reading the latches and opening and closing the latches. So it's really very difficult to detect this, and you can hide the data in almost every part. So now that I have explained a little bit of the steps, we are going to start seeing how difficult will be to create our own malware. And we will perform all these steps in practice. So let's start with the use case. Let's suppose that we are in a company that have modern operating systems, like for example Windows 10. We know where in the intranet where the employees are. We know that the administrator regularly manages some servers that are in other network that have some information, and he does that from the intranet where are the employees. And what we want is to access that servers and extracts some information from that servers. But we can access from our network. We can access the servers because there is a firewall. But we know that the administrator here manage that services through some protocols. Like for example, he used the remote registry protocol of Windows to manage the registry of the machines and things like that. So, what are we going to do? First of all, we are going to use an entry point that will be make a man in the middle in the Windows remote registry protocol. We know that the administrator perform some actions in the remote machine, in the registry of the remote machines via the Windows remote registry protocol, and we will use that. This security issue is something like is something that I have presented the last weekend in TorCon in San Diego, and that I want to show you because I think that is an original entry point that is related with phishing and all that things. And after that, we are going to exploit that machines when we have access. We are going to perform something that is that have been very shown the last months. That is the UAC bypass. I don't know if somebody here heard about it. And after that, we are going to gain some persistence by inserting in the Windows registry of the server machine. And after that, we will open a reverse connection that we are going to handle just with Metasploit in the attacker machine. So I'm going to perform this just for showing you that you can almost build a malware without knowing nothing and without coding almost nothing. So the first step, the entry point, intercepting between the communication between the client and the server. We have said that we are in the same network that the administrator that manage that servers, and that we want to intercept the packages that belongs to the remote registry protocol. So when that administrator wants to set a key in one of the remote machines, we are going to intercept that packet, modify that packet, and insert our own payload so we can have access to that machine. So first of all, what we will perform is an ARP spoofing, so we can start seeing all the traffic that is flowing between the client and the server, between the administrator and the server that is managing. All the packages will go through the remote machine. And after that, what we are going to use is the WinReg man in the middle for modifying that packages that are passing through us. So just a big point, a small point here about how the WinReg man in the middle tool works. That's a tool that will be published this week. I will publish in my GitHub repository so you can look at it. But mostly what it does is when a client sends a packet to a server and that packet belongs to the Windows Remote Registry Protocol, the attacker machine will filter that packet, will send that packet to user space. So in user space, because the package normally flows in kernel mode, on kernel space, so in user space, what we're going to do is modify that packet in the air. We are going to modify the data values of that package, the data fields. We are going to introduce our own payload, and we are going to forward that packet to the server, all in the air. So the same package that go from the client to the server is the same package that is modified and forward to the server. Okay. So after that, we are going to make some privilege escalation. And for doing this, what we are going to do is, first of all, we are going to start a server in the attacker machine. In that server, we are going to put a script, and in that script, what we are going to do is perform a UAC fileless bypass. So when we insert the payload in the package that belongs to the remote registry protocol, that packet will go to the server machine, will be inserted in the room key. When the server machine restarts, the payload will execute, will query to our server that is in the attacker machine, will download the file that we have placed in our server machine, and that script will execute an UIC bypass. That UIC bypass, what we'll do is performing a reverse connection to attacker machine. So first of all, what are a fileless UIC bypass? So UIC is an authorization mechanism that is implemented in all Windows, and that all here have seen it, is the screen that appears when you execute something like an administrator and prompts you some credentials or prompts you for an OK. And the special thing that it has is that when a process executes something like administrator in Windows, it will have an administrator token, and that token will be inherited by the childs that are made from this process. So if this process that has the administrator token has a child, that child will have the administrator token. So some parts of the registry can be modified by a user that don't have administrator privilege, and some parts of the registry you need to have the administrator token for modifying it. The problem here is that HKCU, that is the part that belongs to the current user and can be modified from a user without administration privilege, have some binaries or have some paths where they are some binaries, or the path to some binaries that some programs that have administration privilege query. So if we modify with user privilege that paths of the registry, that keys, and we execute that binary of Windows that query that path with administration privilege, it will create a child that will inherit the administrator token. So if we, for example, in that path, we put PowerShell.exe, when we execute a program that query that path, the PowerShell will be executed with administrator privilege, because it will inherit that token. You can see a lot more about this in internet, and also in El Lado del Mal and other blogs. I have published some things, and a lot of researchers have published. So the malicious code that will perform this UIC bypass is that one. You don't have to understand all. What they're going to do is simply, this is the script that will be in the server of the attacker that will query the machine the victim machine, and that will, what it's going to do is just insert in that registry path the payload that we want to call with administration privilege. So the payload that we want to call is just this one that what we will do is opening a reverse connection to our attacker machine. Okay. So for the persistence, we will just, at the first of all, when we take the package of the remote registry protocol that will insert a value in the server machine, we will intercept that package, and we will change the path where the administrator wants to insert that value, and we will insert it in the room key. So every time the machine restarts, our payload will be executed. After that, we will just need to open the back channel. I showed you in the last slide how we'll open that. But basically, we will to open a TCP reverse connection that we will handle in attacker machine with a Metasploit module. So now we are going to perform all these steps in practice to show you how can be performed. I don't know if you can hear me with that microphone. Yes? Okay. First of all, what we are looking here is, here we have a Windows 10 that is the administrator machine. The administrator is here in this machine and is managing this machine. We are going to suppose that this is the server machine that we want to attack, that we want to extract data from here, and that this is the machine of the administrator that is, for example, managing some keys of the registry of this machine and all that things. Here we have the attacker machine that is in the same network of that machine, and that will intercept the communication and is our machine. So, first of all, what we will need to perform is the ARP spoofing for getting all the packets that flows from the administrator machine to the server machine that he is managing. So we need to know, for example, the IP address of that machine, 100.0.1. Of course, for the demo, I just put the 3 machines in the same network, but this normally will be performed between, for example, the administrator machine and the router, or something like that. So this machine is the 100, we can see it here, and we will just perform here the ARP spoofing between the two. For performing that, we will just use the man-in-the-middle framework. I think that all body here knows how to do that, but I will show you just in case you don't know. You will just put the IP address of the 2 machines that you want to intercept the packets, and it will just join the Ethernet address of that machine to the IP address of the attacker machine, so the packets go through it. So we'll just execute that, and from now, all the packages that flow from the administrator machine to the server machine that we want to attack are going through our attacker machine. Okay, so I'm going to show you how you can use the remote registry protocol for setting some values in a remote machine that is normally used. You will need to open the regedit binary, that is original binary from Windows, and you just put here the IP address of the remote machine that you want to manage. So in this case is the 100. It will prompt you for credentials. And as we can look, we have here all the registry of the remote machine. So for example, if we open the registry in the remote machine, just for showing you, if you go to app events, you can see that I have put here attacker value, so I can change that and put, for example, test. And if I go to the remote machine, I can look that the value of the registry have changed. So what we want to make now, you have to think that all these packages, that set value package, have go through the attacker machine. So we want to intercept that value, modify the path of the registry where we are going to write the value, and modify the value. So we are going to insert our payload in a different key of the registry of the server machine. Okay, for doing that, what we are going to use is just the tool that I have talked before, the man-in-the-middle WinReg tool that works, that is very simple. First of all, we need to establish some IP tables rules that just will redirect all the packages that goes through that belongs to the Windows Remote Registry Protocol to NetFilter, so NetFilter can redirect that packages to user mode and our tool will catch it. So execute the tool, just like this, and in this state the tool will start monitoring all the actions that in this case the administrator is taking in the server machine, in the legitimate server machine. So for example, I forgot to execute the rules. So for example, if the administrator starts looking other keys, just opening keys and looking the values, our tool in the attacker machine will be monitoring all that keys that the client is open or the administrator is open in the original server machine. In the moment that we want to insert a value, we can tell the tool that the next set value that the administrator or the client machine sets, I want to intercept that packet, modify the key where that set value will be performed, and modify the value so we can set another or custom payload. So I will show you the payload that we are going to insert. I want to clarify that I am performing all these steps manual and one by one because I want you to show that, but that can be performed fully automatically. So I can release a binary that performs all this automatically, so you don't need human interaction. So I will show you the payload. As we can see, what we are going to do is just call the winner man in the middle tool. After that, we are going to say, okay, the key that the original user is trying to set, I want to modify that value and set that other value, that is the room key. So every time the server restarts, it will execute our payload. And the payload that I want to execute, I want to modify the value also of the packet. And if you are setting a string, I want you to modify that string and set that one instead. That is that just what this is going to do is query or attacker machine or attacker server for downloading that script that will perform the UAC bypass. So for doing this, it's very simple. We just, for example, here is monitoring. We just execute that with a minus minus key and minus minus value. We can modify the key where the packet will be writing and the value that that packet will write. So for example, when here the administrator goes to APP events and it says, okay, I'm going to set here a test value, nothing happens, all goes well, it can continue going through the registry, but what really happens is that our tool, the attacker machine, has intercepted that packet, has modified that packet, has modified the key IPP events and have put there the room key, and have modified the value test of that package and have inserted the payload. So now that payload is here in the registry. If we look at the registry, we can see that here in APP events is that, but if we go to the room key, we can see that our payload has been inserted in that key. So we have modified that packet. We will just need to set our attacker server, that can be, for example, an Apache, simple Apache, and place the script in that server. So just by doing that, very simple, we have there the payload that we want to download from that machine. So when the original machine that the attacker don't have any interaction with that machine because it's in another network, it just have modified the traffic that flows from the original administrator to that machine that is in another network. With that machine restart, what will happen is that it will query the room key and it will open the reverse connection to the server. So we are going to execute that Metasploit for handling that reverse connection. You can use almost anything here. I use Metasploit because it's simple, but it's a little bit noisy. Let's wait. Okay, so let's use web delivery. Okay, so we have just the handler for the reverse connection in our attacker machine. So that machine have been restarted, and if all goes well, when that machine starts, it will execute the payload that we have inserted previously by the Windows Remote Registry Protocol, and it will make a reverse connection to our attacker machine. We can show that something is executing in the server machine, in the original machine, and that after that we are receiving some reverse connection to our attacker machine. So if we take that connection and we perform a get system, we can see that now we are in the okay, I don't know the command, but we are in the remote machine with the biggest privilege that we can. That's because the payload that we have inserted in the registry have been executed in the room key, and that payload have downloaded the other payload that we have in our attacker machine, in our server, that have performed an UAC bypass in that original machine for escalation, for privilege escalation, and with that privilege, it have performed the reverse connection to our attacker machine, and we have handled that reverse connection in the attacker machine. So now we have the back channel established, and we can do whatever we want. We are almost with the biggest privilege in the server machine. We can deliver a ransomware to cipher that, we can exfiltrate data, we can do whatever. So what's the point here? So the point that I want to show you is that I have just established a reverse connection with all the privilege from a Windows 10 system that I don't have any interaction with that machine. And it's the last operating system that Windows have nowadays. And all this that I have performed, I almost not execute a line of code. I just use some man-in-the-middle framework, the WinRec man-in-the-middle. I write some 5 to 10 lines of PowerShell in a script, and just like that, we can perform a reverse connection. So this will be, for example, a little bit ugly malware, but something like that. So the problem here, just for end my presentation, is about protections. How I talked before, from the time that an exploit or a security issue is released to the time that security issue is fixed, pass a lot of time. So that time can be used, for example, now the Windows Remote Registry Protocol goes on Cipher. So if sometime in the future Windows cipher that protocols by default, this attack can be performed. But in the space from that attack is released to the ciphering by default of that protocol, you can perform this attack in a lot of machines that they are vulnerable. So what I think that is needed for protect all the machines about all these threats. First of all, I think that the static protection that nowadays, for example, the AV or the IPs or IDs perform is something that is very, very difficult to maintain, because you have to release all time some things and some patterns for detect a very concrete malware or a family. Then after some time, somebody modify that malware or take some pieces of that malware, create other malware, and other time to reverse engineer that malware to release some some patches, some things, some patterns for detect it, and all time like that. So I think that other problem is the time that is consumed between the release of the malware and the release of the patches. And one thing that I have seen in the last 2 years is that, for example, 2 years ago, when you go to some security event, like for example to Black Hat or something like that, you will not see any talk or any tool about machine learning applied to security, or very little. Last year, I saw some talks and some tools that treat that the machine learning in the security industry. And this year, it have been a lot, like 3 or 4 talks and some tools, and I think that that is something that is going to be, well, it's happening now, but I think that in the future will be mature to use it in companies and to use it in our own machines. So that's because, for example, what we can do with machine learning is making a profile of our computer or something like that, or of our network, and establish the normal behavior of our computer or of our network, and we will, for example, use some anomaly detection algorithms or something like that, it don't need to know exactly what malware family it have to detect, but it knows that something strange happens. For example, when a reverse TCP connections occur, or when some malware is ciphering, or when an exploit is executing. If you, for example, never use administration privilege, and it seems that you are using administration privilege, that is some strange things that can detect some malware execution. So I think that the protection goes from there. Other trends goes also from virtualization and things like that, but I believe in machine learning. So that's all for me. Thank you so much for attending to my talk. And if you have any question, I will answer you here, or you can write me to my email or wherever. Thank you. Any question?
Thank you very much, Santiago. That was interesting. Following our schedule, the next topic is about computer security also, but it's not the typical computer security issue. It's about something that maybe sometimes we forget, but it's so important to do. It's not like black box. It's more reviewing code, doing analysis on code, and finding flaws before the code gets compiled and then gets on production, which is an important topic. We will have Seth Law talking about code reviewing and application security, but we will wait 5 minutes. If you want to grab coffee, come back, we'll be here. So in 5 minutes, Seth will be up the stage and perform this talk. Thank you very much for coming.
Test. Test. Test.
Sí, sí. So we will follow with our schedule. This is Mr. Seth Lowe, comes from the United States, and he will talk about application security, which is an important topic nowadays because the main component of a network are, in fact, programs, applications. So we have to focus on their security. So thank you very much for coming.
Hello, hello. Everybody hear me okay? I'm not sure. We'll work with the mic. All right. We're talking about application security. Like Pao said, it's very important. Obviously, everything that runs on your network at some point is an application. But we'll just dive right into it, right? I'll talk about why I'm talking about robots here in a little bit when it comes to application security and how we can solve some problems using security testing rather than exploitation or some other way of discovering vulnerabilities. By way of introduction, a couple of, like last year, I was talking on Twitter. Somebody decided that I looked like Mr. Robot because of my Twitter profile. So just to make sure that everyone is straight as we move on. Everyone here seen Mr. Robot, right? Do we know what Mr. Robot is? Okay, good, good. We got some interaction going, good. Somebody's willing to raise their hand? Just to make sure, right? I am the one on the left. I am not the one on the right, okay? We can go back to this if you get confused a little bit later, but we'll move on for now. All right, realistically, who am I? I'm from Salt Lake City, Utah. I know we've got quite a contingent here from Salt Lake City or from Utah in general. You know, we've got a great community there. Neil is obviously spoken already, and there's a couple others that are here with us. I focus on application security, and I have for a number of years. I started out as a developer. That is my background. I moved a little bit into the network security side of things, but tried and true, I like developing applications. I'm the creator of the Hacker Tracker iOS application for DEF CON. That's the application everybody installs on their phones to track the schedule and to make sure they know where they're going. I've been a security engineer, a consultant, obviously a speaker. This is a presentation I've given in the past at Black Hat and other places. Most importantly for Spain, I enjoy soccer. The main reason I came was to go to a Barcelona match, right, this weekend. That's the real reason, not to, okay, never mind. But if you want to talk about it, I'd love to, about why Neymar moved or whatever, right? I track it pretty heavily, probably unhealthily, right? I probably shouldn't do it quite so much. But that's who I am. My background as a developer, I actually came up, I worked at iOmega. Now, does anyone here know who iOmega is? Okay, Lance is raising his hand in the background, in the back there. Great. iOmega was a company about 15 years ago. Do you remember a zip drive? Physical media, you know, we used to actually have to use like these spinning disks to store data. Okay, so I worked at iOmega. That's where I came up as a developer and as, you know, first touched security code. My first SQL injection attack we experienced while I was at iOmega, and that's what got me interested in security and pushed me more along those lines. And actually it goes further back than that. We can talk about the BBS days here in a little bit. But that's who I am. That's why I'm here talking to you. I've been around for a while, and hopefully we'll be here for another while. But remember, I'm the one on the left, okay? All right. So today we're going to talk about security unit testing. Now this doesn't sound all that sexy, right? I mean, it's just, we're finding flaws, we're finding vulnerabilities, but I want to talk about it in a little different way than we usually do, right? Most people already run some sort of security testing, right? So why are we talking about it yet again? That's what I want to discuss, right? As a developer, the goals that come out of the security team are not always the same thing as the goals of development. If I'm building an application, I'm driven by features. Security is supposed to be a feature, but it's often an afterthought, and we don't like that as application security professionals. We're trying to build our security into the products before they move on, or before we actually release them, or they even get to the stage that we're developing them. But the development goals, the business goals, don't always line up with those security goals. As a business and as a developer, I want to create a product, and I want to get it to market as quickly as possible so that I can sell it and make money back. But that doesn't always line up with something actually being secure. And you'll run into this over your career depending on where you're at and what you're doing. These two organizations are often at odds, and they kind of fight against each other. I've seen this in multiple organizations. In addition, the security tools that exist don't always fit the development pipeline, right? If you think about how you find vulnerabilities and how we do as an industry, it's often very manual and it's very labor intensive. So if I am, manually going in and trying to find the OWASP top 10 vulnerabilities in an application, that's going to take days, right? As a security consultant, our typical engagement is about 2 weeks. As a developer, 2 weeks is too long, right? If I have to wait 2 weeks to fix a problem, that's 2 weeks that I am missing my deadlines. So security is often not fast enough for what business and development needs. So what I'm going to suggest today is we can solve these problems with these test-driven development tools. We can integrate security into our development pipeline. There's multiple ways that we can do that. There's tools that are out there that are available. I've also written something that we've used, or that I've used in the past in a CI pipeline to actually speed up testing. And it all goes back to the goals, what you're trying to achieve by finding vulnerabilities. Okay? And this is what I want you to take away from my talk. Flaws, not exploits. As a developer, I don't really care that you can exploit my application. I don't, right? Yes, it concerns me that you can dump all of the data, all of my customers' information, and obviously that's a huge concern to the business, but for me to actually fix the problem, I don't need to know that you can exploit it. All I need to know is that a flaw exists and where and how to reproduce that flaw. So you don't have to go the whole route of, dumping all of that data for me to know that the problem exists and for me to actually start working on it. And so that's where I'm going to flip the normal security testing paradigm on its head. I don't care if it's vulnerable. I care that there is a flaw there. So what we're going to do is we're going to create a little army of bots, right, in our security pipeline or our development pipeline, and we're going to use those bots to focus on one single problem and give us information on whether or not a flaw exists as opposed to a vulnerability. Okay? So the agenda for today, I'm going to talk a little bit first about the current security testing tools, what's out there, what's available, and how it's used. And then I'm going to tie that to the developer side of things, the unit testing frameworks. So you can build these tools, these bots, into your testing methodology as it already exists. But I'm going to talk about how we build those security unit tests, like what the requirements are, what the approach normally is, and then I'm going to introduce you to Sputter, which is a Python-based test runner that takes JSON input and runs security tests based on that. So it'll spin up a bunch of these security bots for you, but in general it follows this approach that I've taken here. And then it's all open source. You'll be able to see it. I'll show it to you. I'll demo it here in a little bit. So current security testing tools. Who here has played with a security testing tool? Have you run Metasploit? Right? Okay, a couple hands. Or like Burp Suite, maybe? All right, there's a few. Obviously, these are these target specific needs in your SDLC. If you've run Nmap before, that's a security testing tool, right? I mean, you can integrate that into your pipeline to test and see, hey, I spin up an application. How does that actually affect my network profile, right? That's what Nmap would do for you. Burp Suite is very similar. It runs against an application. It'll tell you what that application is vulnerable to, but it does go the full route of finding a vulnerability and not just the flaw that I'm going to introduce here in a little bit. Typical security testing tools are all about that vulnerability identification, and they use exploitation as false positive reduction, right? So if I want to know whether or not your application is vulnerable to cross-site scripting, everybody here heard of cross-site scripting before? All right, a few. Lance, I appreciate you raising your hand every single time, yeah? All right, so cross-site scripting is a common web application vulnerability. But what Burp Suite and the other testing tools do is they actually send a payload to your application, a cross-site scripting payload, and they examine the response as it comes back to see whether or not it's vulnerable, right? Now, if the response fires off a JavaScript payload, then they say, hey, we know that this is vulnerable, but what you'll see is that they test multiple payloads. They test multiple vulnerable vulnerabilities or exploits of the vulnerability rather than just testing for the payload like we'll introduce here in a little bit. So they're often very easy to use, right? Nmap is just a simple, hey, Nmap this IP address. Burp Suite is very similar. You point your web browser at it, and it'll actually examine all the traffic, send new security tests to the application. But it's often very hard to absorb the results. If you've ever done a penetration test before, right, that's always the difficult part, right? I have all of this information that's come to me from the tool. How do I actually take that as a developer and make changes to my application? It doesn't go to the code level. It goes often to just the running level, and that may run through some sort of proxy or something else. So it can be difficult to actually examine that and implement those recommendations. The security testing tools are often driven by compliance needs. We're trying to make sure that we adhere to PCI, right? That we've covered the OWASP top 10. This is kind of the business problem that we have with security tools, is they don't always really address security, they address compliance, which is a different need. These include both static and dynamic analysis tools. So we've talked about the static ones like Nmap, like Burp Suite Pro. There's other, those are dynamic, sorry. The static tools would be something like Fortify or CodeWorks, or Fortify, AppScan Source, if anyone's heard of those before. Some of those get really expensive, though, so we'll talk about those shortly. Realistically, this is where they fit in a typical waterfall development model. The static tools are earlier in the process, so as someone's developing a product, the static tools actually look at the code themselves and attempt to determine whether or not a vulnerability exists. The dynamic tools can only be run against a running application. So that's done typically in a testing phase or a maintenance phase once you've integrated all of the components together. Realistically, this is what it looks like, right? At one end of the desert, we've got our static tools. At the other end, we have our dynamic tools, but there's a whole lot of nothing in there as far as security is concerned. And that's where we need to build a couple more checkpoints into this system. So a dynamic tool, I think I already talked about this a little bit, right? We're interacting with a running application, attempting to identify those vulnerabilities. Very often it's implemented by security and not by development. Now, why is this important? If security implements it, they've got different goals, right? What we discussed initially, there's other things that security is looking for versus what development would be looking for. So if they churn out a report, it may not help the developers. Happens later in the SDLC. The developers don't often have access to these tools, right? If we go pay a whole bunch of money for 2 seats for like Web Inspect, HP has a big product that's called Web Inspect that does dynamic testing. Very often, we're not going to give access to that tool to the developers themselves. We're going to give it to security or somebody else and have them dump a report for the developers, which means the developers aren't going to be running this very often. They're not going to see it. Realistically, you know, security testers, all you are is glorified QA testers, right? Quality assurance testers. This is a glorified quality assurance integration test, if you look at it from a developer's perspective. So on the other hand, we have the static tools, which we often do give developers. We scan the code earlier in that SDLC pipeline. It's integrated with the developer IDE so they can run it whenever they want. But again, like I said, there's kind of a gap between the two when we implement these tools. Yes, the static tools do seem to do fairly well in a continuous integration pipeline, but only if they've been instrumented properly. And that can be a difficult thing. The strengths that we have from these tools is just the fact that they exist, that they check those compliance needs, they do identify vulnerabilities based on the exploits, right? They're regular expression engines. We can often extend them for our needs, and they're pretty quick to actually get up and running in most cases, especially on the dynamic side, right? It's very easy to point a dynamic tool at a website or at an IP address, but it can be more difficult with the static tools to actually be able to build code and instrument code so the scanner can check it out. The weaknesses. It's very often that these tools have some sort of false negatives, right? This is bad from a strict business perspective, right? The last thing that we want to do is tell our customers that we're secure and then get hacked. It's going to happen, but realistically, if the tool cannot determine whether or not it is vulnerable to a specific class of vulnerabilities or exploits, it's very dangerous for us to say that application is secure against SQL injection if we can't actually scan the whole thing for SQL injection. We put a lot of confidence in these tools when in fact they don't give us full coverage. They often go through generic identification. That's what I'm talking about here. The lack of a human component means that we ignore full classes of vulnerabilities. Right? It's very easy to identify something where we send data to the application and get a response back. It's very difficult when it is some sort of authorization problem or something that takes human knowledge to identify. Right? So authentication, authorization. A dumb tool doesn't know whether or not you should be able to access the administration functionality of a website. It just doesn't. Yes, you can do some things to attempt to determine whether or not this tool should have access to that site, but realistically, it's just going to crawl the application and send you back whatever data it knows about for the input and output. So there's certain classes of vulnerabilities that are ignored, those business logic ones. Edge cases are often ignored. If we're talking about the traditional pipeline as a developer, and I only give the security team 2 hours to test my application, do you want to know how many tests that we ignore? And we're going to ignore hundreds of vulnerabilities, right? Just because we don't have the time to manually check for all of those. Cost can be a huge problem here too. If you look at those static tools, especially the more premier ones, we're talking tens of thousands of dollars per seat that a company has to pay to get access to those tools. Now that's not going to be, like for big companies, it's not a huge issue. But for a small startup, someone that's running, a company on a shoestring budget, it's just not going to be, it's not going to be possible to implement some of those tools. So we're going to start looking at open source options and other things that we can do. And that's what brings us to unit testing frameworks. So I'm proposing that we use what the developers already have in place to test for security vulnerabilities. My problem with unit tests is that I see something like this very often. So this is a security unit test, this is a unit test that's been built into an application. I did anonymize it because I didn't want everybody to know that Neil wrote bad code, but that's okay. We'll go on from there. Yeah. So in general, what is this, right? Instead of actually implementing a unit test, all that they're doing is taking the auto-generated one, which is example unit test, which tests whether or not 4 is equal to 2 plus 2. That's great, but we're not actually testing our code at that point. We're testing the compiler. Most of the applications that I see lack a basic unit test. They lack even any sort of development unit test, much less a security unit test. But this is a great way for security to actually get introduced into an application, since the developers know the code better than anyone else, even the security team. So if we want to really identify security vulnerabilities, we want to use the tools that they already have in place. Let's see if I can actually get this. Okay, so unit testing frameworks that are available. We're going to talk about a couple of them. We'll just skim through it quickly. Every language that's out there and every framework has some sort of a unit test option built into it, right? Including mock controllers, third-party libraries that people have built to actually test code, the test runners that are available for us. If you've dealt with Java, there's the JUnit testing framework, there's RoboElectric, .NET has NUnit, there's all sorts of different options available to the developer to make sure their code does what is expected. It covers everything from low-level unit testing, whether or not this function returns a proper integer, to complete integration testing, whether or not you can stand the application all the way up and then interact with it. Java, allows testing without full Spring or other containers, Java Spring in general, and that's an example that we'll look at here in a minute. The framework provides mock objects. You're able to actually stand something up, create objects in it, and test those objects to make sure it is what you expect. And it also includes basic reflection tests, access to MVC, which is the model view controller, the full way, basically the full application. So everything from low level to full integration testing, including access to the JDBC, which is the database. Yeah, we can talk about this more if you want to talk about specifics of the different frameworks. Come down late after, and we'll spin through it. The main thing that I wanted to talk about was kind of the differences in these testing frameworks that exist. ASP.NET by default has the same sort of things that we have in Java Spring. It's not available in all versions of Visual Studio, so unless you're paying money, you may not be able to access it completely. You can mock up the different components. But one thing that I found with ASP.NET is that you have no access to the HTML. The way that it creates the tests, it doesn't give you full access to everything that exists within the HTTP request and response stream. Now, why would this be concerning from a security perspective? Any ideas? I don't know, maybe security headers, right? Maybe cross-site scripting is basically HTML injection. If I don't have HTML, there's no way that I can test whether or not it exists. So I've got to jump through some hoops to actually implement this so that I can security test it properly. Django was a little bit easier. The Python standard unit test library actually creates a full Django instance that you can interact with, including model databases and everything else, a test client that exists. The last one, iOS testing. Has anybody here done iOS development? Not many. Okay. Basically, there's two ways that you can do testing in iOS. Either access to the complete application internals, that's this application driver, or UI touch, which is basically driving the screen like a developer or like a user would. But there's problems with each of those depending on what you want to test. The summary here, basically the functionality. Unit tests often focus on the low-level functionality, whereas integration test frameworks provide a full stack approach. When we're doing a security unit test, we're really doing a security integration test, right? And that's what I want to talk about here. We want to actually inoculate our application, right? We're using, I've got like a shot up here. This is what we want to do to our application, right? We want to inject some sort of security into it sooner rather than later so that we don't get exploited when it really comes down to it. So the requirements for building these tests, the application should run in a production-like state. You're creating an integration test, similar to what QA would be doing to test whether or not they can input an address into a certain field. Right? And that includes full full HTTP request response, and rendered HTML. It actually has to spit back something. And that's where ASP.NET, that's where we have a little bit of a problem there when I was talking earlier. We've got to maintain authentication state. So this is part of that full-blown integration, right? We've got to be able to perform authentication and authorization functions. I talked a little bit about the business logic problems and the fact that a human has to be involved. A developer knows where these functions exist, are going to be able to write these tests, whereas a tool is not going to be able to automatically discover where it's at. So we need a working client and application. The full vulnerability classes depend on this functionality. So anything log in, log out, whether or not someone can access a portion of the application, that's all very important for a security unit test. And finally, consistent responses. Applications should maintain state. So if I insert something into the application, I should be able to look that up the next time that I access that portion of the application. Allow for multiple calls in one single test. I mean, if we're doing a full integration test, obviously this would be available. Okay, so here's an example of a Java Spring unit test that actually spins up an environment. It's fairly easy if you can read Java. All we do is implement the class itself that we've created for that application. We spin it up on a random port, right? That's that Spring Boot test, which actually does everything that you would expect, and then we run our injection test after that. ASP.NET is a little different. It's more difficult to actually spin that up. This is getting around the problem that I introduced previously, which is we have to actually spawn up a separate process. Let's see, does that actually work? Yeah. You'll see that here. I actually have to spin up IIS external from the test itself to interact with the application and test whether or not whether or not the vulnerability exists, right? So I've got to figure out how to do that programmatically rather than depending on the unit testing framework for it. Django is a lot easier. I mean, it does something similar, but just the fact that we're doing a test case, it is Django. It knows that it can spin that up, and I can interact with the client here, like log in, log out. We're testing the caching in this case, but it's very easy to do as opposed so Java Spring and Django were very easy, whereas .NET was more difficult. All right, so the reason that this kind of came up in my career or in what I've been doing, we were building courses, right? We were attempting to test code that students submitted back to us to know whether or not they had fixed security issues. So each time that we created a vulnerable application that the students would fix and then submit back to us, we found that we were having to create multiple different unit tests in each of the different languages. We spent as much time meeting these requirements that we came up to as actually writing the tests themselves. It takes a long time to meet the requirements and figure out how do we need to implement each of these in each of the different languages. And it's really a combination of dynamic and static security testing, right? We've got our own dynamic environment that we have to set up, but we're creating static rules around that. We're combining those. Remember that vast wasteland I showed before? We're combining, or we're trying to jump right into the middle of that and actually write our tests and test the code. All right, so the approach that we want to take for security testing, right? Just because you build one security unit test does not mean you've got an impenetrable application. You've got to test each endpoint, each parameter, each vulnerability, and each possible vulnerability payload. If you look at any of the dynamic tools that are out there, this can take a long time. You know, math is hard because if we look at 10 endpoints, 10 parameters, 10 vulnerabilities, and 5 payloads, right? All of a sudden that's 5,000 tests. That's going to take, it could take longer than you expect. Obviously, this is contrived. You know, 5,000 tests doesn't seem like a lot, but if you multiply this across, you know, if you instead of 10 endpoints, you've got 500 endpoints, all of a sudden this test takes a long time. It's not something that you're going to be able to turn around and give a developer a, yes, you can run on that in 5 minutes. It's probably going to be more like a couple of hours to run through that, which may or may not be a bad thing. If we're testing realistically, it's identify the endpoints, create the test for each variation, and run those tests. Identify often looks like this from a security perspective. Like you're trying to find this one needle in the haystack on how do I know which vulnerability that I need to test for this endpoint. As a tool, it's very hard to do this. But as a developer, guess what? They built that haystack themselves. They probably can do this a lot quicker than your tool can or your security team can. Create the unit tests, right? Chuck Norris may be able to do it with a single assert. I don't think he does security unit testing. He makes us do that for him. But it's not too difficult to create these. Once you've identified them, they're a lot easier to create. And then we're going to spin up our different bots, right, to actually go out and test each of those endpoints, each of those vulnerabilities. All right, so I've kind of established, this process that we're going to use. So that takes us to the security payload unit test repository runner, what I'm calling Sputter. It's out and available on GitHub. But the whole reason behind this was these intentionally vulnerable applications that we wanted to test for security problems. We had built security problems into an application. I know that seems counterintuitive, right? We're creating security vulnerabilities, but for learning purposes, for students to be able to go in and fix them, we know where they are, but we have to know whether or not they've fixed them, right? So we had to create security payloads that tested our application, like a developer would create, to see whether or not those vulnerabilities were fixed. Now, we're grading an application. Do you think a student wants to wait 2 hours for a response on whether or not they've fixed a problem? No, right? At most, we wanted all of our tests to run within under 1 minute. So if someone was to submit an application back to us with fixed code, we wanted to turn around and respond within a minute to know whether or not they had fixed the problems and then tell them where they still needed to go. So we had to speed up our security integration into the SDLC because of the response time that students expect when they are trying to actively fix code. So we've used Sputter to do this. We've also implemented security unit tests built into the frameworks themselves. But Sputter is, kind of the intention there. Now, one thing that we found is that we don't have to test for every single case. Remember when I said flaws, not exploits, right? So I kind of want to go back a little bit, years and years ago in my own career, and talk about why flaws are more important than exploits. But I got a little story about this, right? Now, what is this? What is this sign? What do we use it for? For Twitter, that's right. Before Twitter, what did we use this for? Yes, we use it for links. Okay, keep going back. Remember, Neil yesterday talked about these phones that were on the wall that we put coins in. What do you think that number sign was used for there? You're not old enough. Okay, yeah, that's true. That's true. I do have a little bit of gray in my hair. And it's not from soccer. Yeah. Yeah, I think about, dialing into a web, or I say a web, right? Dialing into a phone meeting, right? You put in some number and you hit the pound key and it tells it that you've finished entering your number, right? And then the system does something. So back when I was in high school, yes, this was years and years ago, the administration decided that they were going to implement a system that parents could use to actually dial in and get messages, but it would also call parents when students missed classes, right? So if you happen to skip class, this system would call your house after school, and if your parents happened to pick up the phone, they'd get a little message that said, your son or daughter missed a class today, and we wanted you to know about it, right? Now, is that a good thing if you're skipping class a lot? No, it's not, right? But luckily, they had a phone number that you could call up and kind of you could figure out, or you could actually go log in, get messages from the system, any announcements that the administration wanted to send out, or also check to see whether or not your student had skipped class that day or had missed a class, whatever, clear their absences. You could dial up and actually interact with it. Now, when you talk about, me in high school, running around with a group of friends, there's 3 or 4 of us. We have nothing but time on our hands, and we dial into the system. We can check and hear what the announcements are, but all of a sudden we hit this number sign, this hashtag sign. What do you think happens to the system when I hit hashtag after I've dialed into it? Close. You get some sort of menu. What we got was, please enter the administrator code. Okay, so this is back way, way, way long ago. How many digits do you think the administrator code would be? 4, of course, because that's the most secure number of all the numbers is 4. All right, so what we've got is a system that only takes 4 numbers. We've got motivation, because we don't want our parents to know that we're skipping class, and we have nothing but time on our hands. So what do? We pick up that phone. How long do you think it took 4 guys over a weekend to figure out what that number was? First time it was probably about 6 hours, right? We split up the numbers, 0, 0, 0, 0 through 2,500 were me. My friend Jason took 2,600 to 5,000. Ryan took the, you know what I mean? So we just split it up, and then one of us figured it out. And what do you think we could do? What was in the administrator section of this, this application? Delete. Well, delete wasn't there, right? Which was sad. But something that was almost as good was restart. Because what happens to memory when you restart an application? It's all gone. So all those numbers that the secretary would load into the system at about 3 o'clock in the afternoon would get cleared out when we went in and hit restart at 3:15, right? So it would never actually call our parents when we had exploited this system and we'd reset it. Now, we used this for, I think it was probably about 2.5 years. Eventually, you just don't care anymore if it calls your parents. But, the first couple of times it was awesome because we'd just be like, hey, guess what? So-and-so skipped a class today. Will you reset the system so it doesn't actually call out? Sure. And, every 6 months or so, they would reset the administrator passcode. But, again, we have nothing but time because all we do is we sit around and play on our computers and, happen to be able to figure out what that was. And then, this sort of system still exists, but granted, now they're up to 6 characters, so no one would ever be able to figure that out. No. All right, so why is that important? What does the hashtag have to do with security testing? Any ideas? Do I actually have to restart the system to know whether or not there's a problem with it? This is a traditional authentication or authorization issue with an application nowadays, right? If I can access the administrator section, but I shouldn't have rights to access that, I can abuse it. So I don't necessarily need to exploit this phone system to know that there's a problem as a developer, right? I should have had some sort of an access control check on that front to see whether or not they were coming from a valid phone number, right? Before I gave them access to the prompt to put in their password or put in that passcode. And that's what Sputter is attempting to do as well with security payloads. So instead of, giving, depending on a payload to do everything from the pound sign to putting in all of the digits, running through 1,000 or 10,000 different numbers to figure out whether or not it's vulnerable to this attack, all I have to put in is one single request, that hashtag or that number sign, to see whether or not I can access that portion of the application, and then I can tell the developer that there is a problem there. So we're going to extrapolate that to current exploits and current vulnerabilities that exist. We're going to use generic escape sequences and payloads to test our application rather than specific ones. We're going to focus on the application response more than the input itself. So again, I don't care if you can exploit my application. I care whether or not there's a flaw there that exists. So if we look at the payloads from FuzzDB, is everyone here, has anyone heard of FuzzDB before? Okay, there's a couple of you. What is it? Well. Mm-hmm. Yes, exactly. So it's a list of payloads that's open source that anyone can download and then throw against their application to see whether or not it's vulnerable to SQL injection, cross-site scripting, buffer overflows, right? Anything that is security related is in this list, and there are all sorts of different payloads that exist, right? So this is the beginning of the cross-site scripting payloads. There's something like 250 of these, right? So if you think about the math that we did previously, right? Every endpoint that may be vulnerable to cross-site scripting, if we're using the FuzzDB list, we are going to have to run 250 separate tests, separate little bots, to actually check to see whether or not it is vulnerable to cross-site scripting. But, I mean, if you look at these first 16 payloads, the one thing that you'll notice, if I'm only looking for flaws, the only thing that I need to check is that first character. I may have to check like 2 or 3 more, but realistically, if this comes back unencoded into my, my test runner, I know that there is a problem, and I can tell the developer to go fix it. So I can take these 16 payloads, and I can sum them down into 4 different tests. Now, can you see how we've just reduced completely the number of payloads that we have to run? Like, I can go examine all of the FuzzDB list and determine what these different payload escape characters are, and I can cut down on what I actually have to test for because I'm not focused on exploitation, I'm focused on flaw finding. And this is exactly the approach that we've taken with Sputter. Right? We're going to examine these 4 characters, and we're going to send payloads for each of those, but we're going to ignore the fact that we're going to ignore the check for the vulnerability and for the exploit itself, and just check for the flaw. So we're focused on the characters and the strings that expose the application, not the exploitation, and we're eliminating redundant testing. Just because you have all those payloads doesn't mean you need to use them to know that there's a problem with your application. So here's an example of a payload from Sputter, right? I'm taking the same approach that actually Burp Suite does when they generate payloads by throwing some random strings around the character that I'm concerned about so that I can use that for identification later. And we'll actually show this really quick. Let's see if we can pull this up. All right. Hold on. All right, so like I said, Sputter is just a Python 3 application. Let's see if I can actually find my string here. Maybe. Okay, so this one I've just created a small test that shows us what the payloads look like, right? So in this case, I'm accessing a task manager application, the search functionality, and I'm checking against the queue parameter to see whether or not it's encoding everything that I'm concerned about. In this case, you'll see that it's not filtered for parameter Q. So I'm only testing for cross-site scripting payloads right here, right, this XSS test. And what you'll see is that it generates that 5-character string, the character that I'm concerned about, the ampersand, greater than, less than sign, and then spits out whether or not it's vulnerable. And if I run it again, you'll see that it changes. So every single time it actually changes that, but you can't actually track it. It stores these results in a format that you can parse later on, because everything that I'm creating here, I want to be able to be consumed by your test-driven development tools, right? And you also, like I do the same thing that any test runner would. This actually creates a standard error output rather than just standard out message. But anyway, so that's actually the payload demo where we're creating those payloads. Let's play from here. Test generation, this becomes more difficult. I can't automate this completely. Remember we had that picture of the haystack and actually identifying all of the endpoints and parameters and vulnerabilities. We can automate some of this for you when we attempt to do it, but it depends on the framework and the application that you're using. Something like Django or Java Spring, it's very easy to actually go in and pull out all the routes, but I don't know which of those, what tests you're going to want to be running on those and the parameters that are associated with it. So someone does have to spend a little bit of time configuring this. I would propose that you push that down on your developers or your QA team as opposed to your security team, because those guys have the best knowledge of how the application is built. But you've just got to map out which parameters and tests to apply to which endpoints. If we look at, all right, so like the payload demo, this is exactly what you'll see. It's just a JSON file. You configure the domain, which is the endpoint itself there, whether or not you need to be authenticated, the different endpoints that exist. This tells it that it actually has to log in. There's credentials that you have to put into the file as well. Those are the tests that you're currently running. Those are the tests that are currently supported by Sputter. But we are expanding that list out, the different parameters that are being checked to see whether or not item is vulnerable to cross-site scripting. But you can throw more in there, right? You could do 10 parameters in there instead of just one. But you can speed that up significantly by using Sputter as opposed to Burp Suite or something else. So that's your generation. Let's see, what time are we at here? Oh, we're moving right along. Okay, I wanted to actually demo the testing itself. Sputter gives you a consistent way to test multiple application frameworks or multiple applications that are built on different languages and frameworks. We were able to implement it in both AWS Code Pipeline and Jenkins. Any test suite that you have or build tool that you have can actually call Sputter. It's just, like I said, Python 3, so it's very easy, and it decreases the cost of building these unit tests because all you have to do is understand JSON. You don't actually have to understand Java. As a QA tester, as a security tester, to actually build a security unit test. So, all right, and then that's sputtering for the future. We'll do a quick test here. Actually, let me show you. Okay, so here I've got an application. This is the task manager application. I've stood it up to actually run a test against it. You're still going to have to automate this, like standing up the application to run the test, and then you can tear it back down. But you'll see right now there's only 4 different projects that are in this task manager application, and we'll see those unit tests actually insert data into the application itself. Right, so if we run our Django test here, there we go. And what you'll notice, this takes a little bit longer because I'm trying to give full coverage to the application rather than just testing a single endpoint. But as a developer, I know which of those endpoints I'm really concerned about when it comes to these different vulnerabilities that I'm checking. Right? An access control test, I know what a developer or what a user should be able to access and whether or not the test should succeed. So I can check that and know that it, in fact, is. I can give a better assurance that the application is vulnerable or not vulnerable to that exploit or to that problem than an automated tool could, right? So you'll see, right, like I'm doing a check here for settings. but you'll see that there's no authentication that's necessary to actually access that settings page. Now that's a problem for this application specifically because that contains administrative detail and including the dashboard as well. Somebody could actually get to that. If we look at the application and the response, what actually goes on here, right? All of a sudden we've got hundreds of different projects that are in there, including ones that have the payloads that we've defined. So if these aren't encoded properly, that did result in some sort of a report and some sort of a result. Okay. I could show you quickly as well. Let's see. The output, right? So if you look at the output, it's in a format, it's JSON just like you would expect from any other tool that's out there. It'll also dump HTML if you want it to, if you want something that's pretty that someone can look at, but that's not as concerning to me, right? So in this case, right, there's those different payloads that we were looking at earlier. It does give a fail there. If we look at some of the other results, right, if the application does something that is not expected, right, if there's a response that, hey, it passes the SQL injection tests that are here, right, but if there's a response that is not, hold on, I lost my mouse. What you'll see is, okay, there's an error in this case, right? Now, when there's an error that happens in any sort of a test, this is telling the developer, whoever's checking the logs, that there's a problem, but that Sputter was not able to determine if that was a vulnerability or if it was just an issue with the application itself. In this case, it's a CSRF check, which means that if there's no CSRF token, I can't actually check to see whether or not an application is vulnerable to a CSRF attack. So I'm going to post an error and say, I don't know about CSRF. It's up to you to determine whether or not you want to actually go fix that, right? So I'm trying to report everything that is possible with the application back to the developers to actually be able to fix it. All right, so sputtering for the future. Whoops. Nah. So what we're doing in the future with Sputter, we've been adding payloads and further refinement, additional vulnerabilities. I keep expanding that list out. Testing speed, speed that up to make sure that the threading is working properly. So that test that I ran against the Django application, or the task manager application, that took a minute and a half to run. With threading, I'm pretty sure that I could get that down to probably 30 seconds or so, pretty easily. Generation, more automated analysis, more frameworks, more languages, maybe a Burp Suite Pro plugin to actually pull in some sort of a list instead of actually having to generate that JSON file by hand. All right, any questions? We'll just give a quick summary and I'll be done. You can be bored to someone else here in a little bit. Yeah. The current security testing tools are great at exploitation and finding vulnerabilities, but not at not all, right? So there's certain vulnerabilities that we want to actually discover that it won't. We can create simple security bots that have the knowledge of developers to actually identify additional flaws and use Sputter and DevOps pipeline to speed up security bot creation. And then remember to use the hashtag. Just push that number every time that you dial a phone number to see what happens, especially an automated system, okay? All right, any questions? Yeah.
So you're saying using Sputter is obviously the most effective with the actual developer themselves using it, but how useful is it if you're not the original writer of the code or you don't know that there are additional, even if you are the writer of the code, you have blind spots that you don't remember what it is that you did?
It does pretty well in that case. So Sputter is still useful. Obviously, a developer is going to be able to tell you quickly whether or not you want to test an endpoint for authorization issues, right? But you can still stand those tests up like you could with a dynamic scanner and let it run to see what the response would be. Whether or not it's actually as useful is going to come down to some sort of a check, a manual check at that point. Okay. Yeah?
I missed the first part of your presentation. So you may already answer this question, but I would like to know, I guess Sputter has like a configuration file when you can customize the rules.
Yes.
Based on which he's gonna, run the test. Is there a way to customize the rules?
Yes, there is. I mean, it's all open source, right? So that you can customize which rules run, right? So if we think about like a login page on an application, right? You're concerned about the inputs on that login page, but you're not concerned about who can access it. So you don't need to run an authorization test or an authentication test because you want that exposed. So you can eliminate those tests and you can just say, hey, I'm concerned about cross-site scripting and cross-site request forgery and the tests that are built in there and SQL injection for now. And you can ignore the other ones. So you can customize it on that level, or you could actually just dig into those tests separately and add them or add additional functionality if you wanted to. Yeah. Yeah. And so here, I'll pop that back up there. Sputter is just out on my GitHub repo. I'm just Seth Law on GitHub. Just like everywhere else, I decided to just dox myself across the internet. So that's who I am, right? Any other questions? No, here. I've got a slide if you want to check that out, but no, I'm not. Green, red, right. Cool. Lance?
Push the developer to develop kind of just a blacklist of I'm just going to fix these characters. Because normally you want to have, for my applications, I try to push more of a whitelist of these are characters you're going to allow, not just what you're going to remove. So I mean, I can understand how it's probably helping with the COs and the flaw, but doesn't it kind of push the developer to just fix those specific characters and not actually focus on
It could. It definitely could, right? Realistically, right? I mean, realistically, I'm building out the payload set, right? So if I am looking for, if we take the XSS payloads, for example, I'm going to be checking some sort of a list against that, right? It's got to be a payload list, and I can expand that out to as many, different character encodings as we want. But at some point, that's coming back to kind of developer education as well. And that's where I would be looking. Like I'm looking at this as, hey, I'm a QA tester. I want to test these, 10 things quickly rather than, or I'm a security tester. I'll let the developers actually build the configuration for it. But I'm going to get the results into my pipeline rather than just on their desktop. So you're still going to have to educate. You're still going to have to teach them what's important and what's not. Cool. All right, and if there's no other questions, then that wraps it up for me. Thanks for having me. Thanks for coming.
Thank you very much. Now we welcome to the stage Lawrence Davis, who will talk about SQL injections, a common attack in modern web applications. Welcome, Lawrence.
can't write to this USB.
Okay, if you email it to me.
I can email it. I have to send it after though. Let me see if I have one. That. Let's try this one. Okay. All right. Let's see. Well, they can't see the slides at all. They can't see the slides at all. If they're streaming, you're just streaming. You're not showing the slides. Okay. Let me fix this then. This guy. Let me just format it. Format. Erase. Name. Okay. Are you using Windows or Mac?
Windows.
So you won't be able to see Mac, huh? So let's see if this works then. Let me email it right after because I don't have internet.
Okay.
Or you need it right now. Okay. Hold on.
Okay. Hey, don't worry, when we upload the video,
What's that?
you will it after, and when we upload the video, when we upload the video, we will put slides next to the video.
Okay.
That's all.
Okay. Oh, very nice. Okay. Let's see. Let's try this one. Hello. You guys hear me okay? Is this thing on? All right. I'll just talk. Where'd it go? It was. Oh, wait. Hello. Nope. Seth, you still his handheld. Powell stole it. Where'd he go? Are we? Hello? All right. Whoa. Now we have sound. Okay. Good morning. So yeah, clear my. All right. So we're going to talk about SQL injection this morning. How many people are familiar with SQL injection? All right. You guys can leave the room. You don't need to talk. So. A little bit about me. So my name is Lawrence Davis. I go by Davis. Been around the community now for a little bit when I found the DC 801 crew back at DEF CON 22, and they just can't get rid of me now. So, so a few things. I like to ride mountain bike. I like to play with slot cars with my son, and hack on anything that I can get my hands on. Some of the things, yeah, like the airplane ride over was pretty fun. I was trying to figure out how this one door worked. And that was a very interesting door because it had a lock on it, had a turn, but it just would open. And so we just went through and left it alone. So, yeah, don't mess with things on airplanes. So a little bit of disclaimer, don't hack your friends, don't hack anyone that you don't have legal rights to. If you don't have permission to touch it, then you should probably not be messing with it at all. There's plenty of vulnerable web applications, vulnerable servers, plenty of people that are creating just little toys and VMs for you guys to play with on the internet. So go download those. Don't potentially try to hack any type of big companies or anything, because they definitely won't like it. Who's familiar with the OWASP Top 10? Awesome, Lance. So a few of you. So OWASP, go out to OWASP.org. They maintain a lot of great information, a lot of details about some of the stuff I'm going to go over today. Come on, wake up. There. Okay. So they have basically they maintain a top 10 list from year to year. I believe they're coming out with a new update pretty soon. The last one was in 2013. One of the largest things that that they look at is basically what are the types of attacks going on. And the one we're discussing today, being SQL injection, is at the top of the list, which falls into the category of SQL injection, command injection, or anything that you can inject into a application. What are you doing, dude? So I'm not sure why this thing keeps going to sleep, but the monitor down here is fine. So what is SQL injection? So SQL injection is basically taking a SQL statement inside of any web application, any we'll leave that alone for a minute. Any type of application that that's connected to a database on the back end. And what it is just basically injecting code that you want the database to execute into that back end. So SQL injection can be from a website that has an input field, can be from an actual application that allows inputs, pretty much anywhere that you can input raw data like a string or numbers or anything, any free fields, yeah, it's freaking out, any free fields that you can input information into a application, you could potentially inject SQL into. So this is a typical SQL statement. This is very common statement to log in a lot of times. So you can see my username and my password up there in red. These are typically spots where you'll inject SQL into, so you can put your own code in and basically try to see what you can do with the database. Like what Steph's talk was showing with some of the fuzzing, some of the other things with SQL injection is you can try fuzzing the database, looking for edge cases in your application to see if there's any exploitable areas in that. It's hot. Okay, come on. All right, so there's three types of SQL injection. The first type is the most common, is basically you inject SQL into a web page or into an injectable point, and then you get instant feedback on that page. That could be an error message. You might be able to dump data from the database. A lot of different things that can go back just in the initial phase. The other type, or two other types, the second type is out of band. So out of band is when you may inject SQL into a web page, or you can inject it into the application, and then the results aren't necessarily going to be back on the web page itself or presented back to you. You might do something to send off like an email, or maybe you want to do a ping or something just to see if you can get the back-end database to react to what you're trying to inject into it. There's a lot of different styles of that as well. It can be some of the tools that use that is, for instance, like SQL Map is a utility that you can use that will try to dynamically map out a schema of the database by using some out-of-band attacks against the database. And then the third one, is inferential, which means that it's kind of basically you can use like a timed attack, or you're just trying to infer the data based on the type of SQL that you're injecting. So you're really going blind on this one. You're not seeing anything coming back to you. You're not getting output somewhere else, like to your own system or anything. You're basically just trying to go against the system, trying to see if you can break it in some way, just by, most of the time, by timing attacks or by other types of injecting SQL into the database. All right, so with that moment, now we're going to do a little bit of demo. And so with the demo, what we're doing is I'm going to show you some simple SQL injection on a web page. We're going to go from basic injection down to actually how we can get a shell on the server itself. So a few steps along the way, we're going to look at some of the database information on the back end and some of the users and some of the other things to show you how dangerous SQL injection can be. Can you guys hear me on this one? Hello?
Yeah.
This one? Okay. All right. Okay. So real quick, the application I'm using, come on. Here we go. Close tab. So the application I'm using is a vulnerable web application from BWAP, which is basically a buggy web application. It comes in a VM that you can download, or you can download just the software itself. There's also some other ones. I used to use Damn Vulnerable Web Application, and there's many others like NodeGoat. There's also WebGoat, which OWASP puts out, and a few others. So I just recently started using this one because I found it a little easier and a little better self-contained. So all this is, we'll go over to the browser. Wow, that's really freaking out. Just a second. Let me break something more. Come on. There. Oh. Are you kidding me? All right. Stop. My apologies. Just a second. Let me see if we can get this thing under control again. Come on. Scaled, there. Default display. All right, let's see if we can get through this demo before it starts freaking out. No. Come on.
Show us through interpretive dance.
I'm not as good of a dancer as you are, Neil. I'll do some jump jacks. Come on. All right, let's see here. What's this other computer got? Let's see.
Do you think it's the adapter?
Oh, it's definitely the adapter.
You need one? You got another one?
You got another one? Yeah, you have a VGA one?
HDMI or? The VGA. Oh. Yeah. It's the VGA that's not working. You're doomed.
Oh, great. All right. Let's try a direct plug again then. Switch again. Come on. All right. How do we connect to this other computer? Let's see. Where'd Seth go? Seth, you still in the room?
think this one will help.
Oh, I don't mind.
And then you go there.
Okay.
Let's
All right.
try this one. I think it's like
Let me leave it alone just for a
it's
second.
like you are doing,
Yeah.
you're going through HDMI and then going. So
Okay.
This one is a shortcut.
All right. It's stable for a minute, so we'll try it, and then, and that's it. Just when we think it's good. Come on. All right, let's try that. Guys, enjoying your day? Is this entertaining?
Tell us a story.
Ah, what kind of story?
I want you to dance.
You dance with me.
I danced yesterday when the same thing happened.
I try, man. All right, just a moment. If we don't get this, I'll figure out a dance. Oh, come on. Come on. Wow, that's an old background. I'll take it. That is a very old background. So we are in extended display. Better than nothing, yeah? Display, where am I at here? Arrangement. This is awesome. I think we'll be good. All right. Cool. Projection. Oh, dance. All right, let's try this now. Stay on, Damien. That's huge. Okay. Can you guys see that okay? Yeah? Because I can zoom it in. I mean, I think it's pretty good, but yeah. All right, so like I was trying to say, man, that really lets us stress out now. So, the Buggy web application is awesome for this. So what it gives us you guys hear me okay? What it gives us is it basically brings in all the OWASP top 10. And so you can try out a lot of different things here. Yeah, a lot of different SQL injections, command injections. You can go into cross-site scripting. Anything in OWASP top 10, it has many examples in here. So I suggest if you're into this stuff and want to learn more, go download some of these tools and just play with them. They'll really help you to get better at it. The one we're going to use today is the SQL injection, and I'm going to use the get search. And the reason why we're using that is so you can see, can you guys see the URL really well? Or do I need to zoom it out? So I want to use the get search because what the difference is, if you just use a post is going to go behind the scenes and it's going to pick up any server variables or any posted variables, and you're never going to see those. But I want to be able to show you what's getting passed to the server, plus it's going to make it a lot easier to see the entire pass that I pass in so that you can get a feel for it. So we're just going to pass it through the URL once we get started. It wants me to log back in. And we don't need to save that password. All right. So go back down here. All right, so this is just a simple search. You're going to search for a movie. If you put in A, it's going to give you anything with A. If you put in Joe, for instance, hiya. If you put in Joe, it's just going to return only Joe, right? If this were an admin login or something, and if we wanted to try something like a simple SQL injection of tick or 1 equal 1, all right. So what we're doing at this point is with the tick, we're going to terminate whatever type of a string that's trying to be inserted in, like the my username that we saw before, the my password. We're going to terminate whatever's going on, and then we're going to just insert an or statement, and we're going to basically say 1 equal 1, or just something that's true. That's all we're looking for. And then we're going to terminate that SQL statement and then comment out the rest of the line. So since we're working, in this case, we're working with a MySQL database, the comment is going to be a pound, a sharp, or a double dash line. But you also need to make sure you have your space after that. If you're working with a different database, then you'd have to know what that back end and what the language is for that. So we're going to inject actual SQL code into the SQL statement. And so when we search, since we've given it a true statement, we get all the data back. So that's the first step, just testing to see if SQL injection is possible. We might have gotten an error here, and then we'd have to do a few more things. In this case, the website's not trapping any errors or anything like that. It's just looking at it, taking whatever input you put in the database, and just giving it back to us. So what we can see in the URL up here is just a little bit more of that. It's just being URL encoded. So now that we have the URL, instead of using the search, we can actually work off the URL and make things a little bit easier. So we're going to do a little jumping back and forth here to bring up my examples. 02, because the next one we're going to do is a union statement. All right. So once we know that SQL injection is possible, what we're going to do, actually let's just stay down here in the search. You guys still see the search okay? So what we're doing now is instead of, we don't care about the data that's coming back. We want to get to more interesting data that's in the database. So we want to jump around into some other tables and start kind of just exploring what the back-end database has. Maybe there's some credit card information, maybe there's some usernames and passwords. If there's passwords, that might be some reuse on some other sites. So there's all types of cool information that we could get out of the database. So what we're going to do is instead of actually doing the true or the or true, we're just going to throw a 1 or a negative number. We just want something in there that's just going to basically error out, because the union statement, which is going to join to other tables, that's what we want to do. We want to join to those other tables and start pulling data out of the tables that aren't coming back. In order to do that, when you use a union statement, you have to select the same number of columns as what the original select statement is. Since we don't know how many columns the original select statement is pulling back, we could kind of guess that we've got, looks like about five columns here, probably an ID somewhere, so that's going to make maybe 6. So we can start jumping around, and we know that, okay, if we union select 1, we expect an error on that, right? Because that's not going to match the column count. And in this case, the error message coming back is just that. It's giving us saying that there's a different number of columns. So then we got to start playing around with it a little bit. And so usually we'll just use static values. And so let's put in, 4 numbers and try that. And so we've still got errors. So some of this is kind of just fuzzing the database a little bit. I know that on this example, it's actually 7 characters. Or 7 columns, so we can go ahead and select that and just kind of short circuit a little bit, and we'll just jump up and do 7 columns. Now, once we have that, it's important to note where the numbers show up, because that's what's going to show up in your column values. So we see that we have 2, 3, 5, and 4, so that's where we want to populate data if we're pulling from a different table. If you populate it somewhere else, it may not show up on the screen, even though those columns are selected. They may be used for something else, or IDs, or other types of information. But in this case, since we have visible numbers, we'll just pick 2 since it seems like the largest column, since that's where we can fit most information, and we'll use that for the next example. All right. So, and this is where it's going to get a little bit deeper. All right, can everyone see the URL at the top? We're going to switch to that so you can see the full select, or the full injection point, or at least most of it. All right, so in this case, what we're going to do is I want to know what the name of the database is, and I want to know who the user of the database is. If the database user is someone like root, or someone with a lot of access or admin access, then we can easily jump into into other databases as well as other tables. So we're not restricted to the current database that we're in. So I want to know what is the current database and who's running that database, who's that process running as. And we're going to put that in columns 2 and columns 3, which will show up in title and release down here. And then we're going to just leave our static numbers in the rest of them. errors somewhere. So one user down. Oh, that's why. Human. Percent syntax. Percent one. Okay. There. All right, so it does need to be, depending on the browser you're working with, sometimes it'll encode it for you. In this case, my browser is not wanting to work with me because nothing else is today. So what we get back is we see that when we selected the 2 and 3 column, so the database, the process is running as root, which means that we will be able to jump into any other databases inside of this instance. And we see that the default database for the application is BWAP, or the Buggy Web Application. So once we have that, the next thing is to look at the MySQL users table. You know, let's stay over here for a second. So what we're going to do next is another thing. If we don't have enough columns, we can actually concatenate fields and pull in the username and the password into the same column instead of breaking it up apart across multiple columns. In this case, what we're going to do is we're going to union again, but we're going to pull from the database table user instead of the current database. So now we're going to jump between two databases. So we're going to terminate the statement in the current database, jump over to the MySQL user table, and then pull whatever usernames and passwords are in there. There's also other information as well, hashes, email addresses, and a few other stuff, but this is all we're interested in for the moment. And so now what we're seeing in our first column is the username and the password. So these are the password hashes. And if we had a cracking machine or some other device, then we could actually take those hashes, especially if they're very simple. Sometimes you can just look them up on Google, and which is the first thing I usually do with a hash. I'll look it up, see if it's already been cracked somewhere. If not, then we can place it there, or place it in our cracking list, and just let a cracking machine go through it. In this case, though, since we know that we have this much access, we can go a little bit farther and see what else we can do with the database. Okay. So another nice method that you can sometimes do with databases is you can load static files. In this case, we're going to try to load the etc password file, or passwd file, which is where all the users, in older system, it was where the passwords were stored as well. Now they're in a shadow file on Linux systems. But for this one, we're just going to load it up and just see what type of system users are actually on the server. So with the etc file, with the passwd file, we can see that we have root. We can see what type of shell root is running in. So we could also get a list of users. We could possibly start trying to use like SSH exploits or other things to try to get to the system, see what else is available. We also see what users actually have shells as well, and what type of shell that they're allowed to log into. Down near the bottom is usually where where user-created users are at. Most of the time, near the top, it's going to be all the system users and anyone else. And then once we get down to the bottom, it's going to be like, for instance, here we can see Neo, Alice, Thor, Wolverine. These users have been created in the system. So if we couldn't get in with root, we could also try other users to see if their passwords are weak, or try different attacks on them. So The other thing that you can do with a SQL database a lot of times, depending on what's enabled on them, is we can also write files output. We can write out to logs, or we can write files out to the file system itself. In this case, this is an example of writing a file out to the file system, and what this file is going to do is it's going to pass any system, any type of system command, like an ls. We could format the database, format the hard drive. We could do anything that the user who's running the database is allowed to execute in the system itself. For this one, I'm just going to write out a command file, so that now I can start sending commands to the server itself and bypassing the web server and bypassing the database. Because now I'm done looking around the database. Now I want to start looking around the server. So in this case, we're going to get an error back. That doesn't necessarily mean that our file didn't write out. If we look at where we were putting the file at, you have to know what database or what folder is writable. Sometimes this can just be a test, or just kind of going through and trying different things. If you know the system has like the ability to upload images or upload other files, sometimes you can look and see where those files are stored, and then kind of get an idea of about where you could put the files at. In this case, we've put our file in the logs folder as c.php. So what we can do is open a new tab and browse over to that file. So we're going to go logs/c.php. If it's there. Oh, BWAP. There we go. So right now, the file that I wrote out, it's erroring out because it's expecting to have a parameter passed to it. Since I didn't pass anything, it's just going to give us an error. So all we have to do is pass in the command we give it, and now we're actually looking at the file system on the server. So since we're in the logs folder, the only thing that we wrote out was the c.php. So we can issue a command. Now we're looking at the root folder on the server. We could go back to our etc passwd like we did before. And basically we can just start navigating around the server just as if we were on it with a command line, except we're going through a web page that we wrote. Once we're at this point, we can take this one step further if we want, or multiple steps further, but at this point we're just going to set up a local netcat listener on port 4444, and then we're going to tell the server, instead of just navigating around, I'm going to tell the server to connect back to my local laptop on 4444, but I also want it to execute a bash shell for me, so now I can interact with it on a command line level versus going through a web page. So we just put that in, let it run, and you can see now we have a connection back that opened on client port 38525. I can ls, I can look at who I am. So the web server, so this is going to be whoever the web server is, the web server process, whoever that's running as, that's who the user is that you're going to be in. So if you're in as root, you've already won, because at that point you don't need to go any farther. You can start manipulating the system, pivoting around, or just jumping through things. Since we're at user www data, then most of the time what we want to do with this is probably look for some type of privilege escalation, or maybe even see what the www data user has access to. For this instance, we're going to stop there, just knowing that at this point we can run commands like uname, see what type of Linux kernel is running, and with having full access to the server, we can look for any type of exploit that might be there and take advantage of it. And then, let's see. So, okay. All right, so that's demo over, and we made it through that. So, So what we're showing is right, SQL can be really dangerous if you let it. And so what we want to really focus on as well, I mean, you're going to have red team, you're going to have them going after things, but we want to look at how we can prevent that. And so there's a few different mechanisms that we can use. So the first one is validating your input, making sure that anything is coming into the database. I mean, just a simple, like Seth was talking about earlier, just a simple check, a few checks of doing either whitelisting or blacklisting will make sure that any data that I would pass through that to that web URL in the first place, for instance, the tick, just a single tick to basically terminate the SQL statement. If we're escaping those type of characters or only allowing, like for instance, alphanumerics in there, since that's a search for movies, we can limit that input, and that's going to stop 90% of these types of attacks just right up front. They're not going to be able to get past it.
So whitelisting and blacklisting.
The other thing which is very important, just because they're using the web server doesn't mean that there isn't a different way in. So whether you're using client-side types of escapes, whitelist and blacklist, you also got to use back-end whitelist and blacklist as well. But you also need to move one step further than that and use parameterized SQL statements. And so that can be calling a stored procedure. That can be just passing parameters to your SQL statement instead of just passing whatever comes from the input queries. It's basically filtering that in so that when you do a prepared statement or parameterized statement, it's going to compile that and it's going to block out any type of the attacks and just do a lot of the escaping for you of the SQL. Or the parameters that are input. I hit on it just a little bit, but along with the parameterized statements, the stored procedures is going to be similar to this. So now the code's executing on the database itself, so you're not doing any SQL inline inside of your web application or any of your applications. All you're doing is calling a stored procedure on the back end, and you're just passing those parameters. Most of the time, those parameters are going to be data typed. So if you're expecting an int, you're going to get an int. If you're expecting a varchar or a date time, you're not going to be able to basically pass some other type of SQL to that stored parameter or stored procedure because it's already going to be filtered out. So, and then as we're looking at inputs, it's also important to encode what's going out. Sometimes just because things come in a certain way through your website or through other means, you're also going to have some other teams that may be doing data integration. So they're not going to look at your website at all. They're not going to follow the normal ways that you get data into the database. They're just going to import it in. And I've had problems in the past with this. I was sitting in a code review where I fixed the encoding going in. So we were whitelisting all the information that was coming in, and I asked the architect I said, okay, this is going to fix this for the website, but are there any other inputs in the entire system that allow data into the database besides this one way? And they assured me that this was not the case. There's no way data can get in. Later on, I found out that the implementation team was actually just dumping data from customers directly into the server, into the database, and so we had a lot of problems on the data that was actually in there. So all of my input blocks, all my blacklists and whitelists were great for the single path, but they didn't do anything for implementation. So you always want to look at what's coming out of the database as well. Make sure you're not getting any type of cross-site scripting that's going on or any other types of attacks. And so you want to encode the outputs as well as inputs. So in summary, basically it's just understanding what your data is, understanding your inputs, your outputs, making sure that that everything is, that could happen. Make sure you block those things, and make sure you sanitize everything. So this is one of my favorite XKCD comics. It's been around for a very long time, Johnny Tables, and just takes effect on naming. And the funny story is that most recently there's someone with an odd name that had some apostrophes in it, and it actually did break the school database at our local school. So they it was pretty funny. So they actually didn't have a way to put their name in correctly, and they had to fix that. So this is some of the references. I'll pass my slides so you can get these as well, but this is just some of the references from some of the research I did, some of the apps and different places where I pulled the data from. And that's all I have. Thanks for patiently wading through everything. So any questions you guys have? Or anything you want to expand on more? All right, I'll get out of here.
Thank you very much. Finally, you did it with the projector and everything.
Yeah.
Sorry for these small technical problems. At least we have some funny things to talk about later. Now we will talk about side channel attacks on embedded devices. We will have the people from Brightside, who are also sponsors of this event. So thank you very much. We will be waiting 5 minutes for Paul and Manel, who are just next to this room, and we'll proceed with our talks. Thank you.
Bueno, portem ordinador, no sé, però bueno, també portem un USB com un PowerPoint. O sigui, què teniu aquí?
Sí, porteu l'ordinador.
Sí, sí, també.
Doncs, quan preferiu. Sí.
El que passa és que a l'ordinador tenim el LibreOffice o l'OpenOffice que no reproduirà les...
Bueno, si teniu aquí un Windows amb tal, doncs ho farem així, i si no, si fem l'ordinador ja està, si no. Sí, jo que tinc un... Sí. Doncs el que veig ja amb els tanta... Ja gaire personal. Que la podem fer... No sé. La podem fer en català. M'encanta quan... O sigui, el que em mola amb ells quan està... Perquè jo sempre no ho faig moltes vegades. Està la sala buida i ja no es pot.
Està tothom desperdigant. No hay mucha gente.
¿No es en serio? Podría encender así.
PDF
no está algo.
Sí, el que passa que com hi ha animacions...
Sí, però funciona igual.
No, espera.
Amb el Beamer, com ho fem nosaltres, funciona igual.
Sí. És animat, no?
Sí, ara
¿Y ahora qué nos da? Ay, la pobre técnica con un manga.
Todo funcionando. Tenim aigua o...?
No puc aconseguir una.
Bueno, si no, vaig a buscar.
Si no et fa res.
Sí, no.
A sobre? Mira que informàtic. Vingui. O sigui, el projector va, em deia no.
Reinicio.
Sí? Perquè no, els altres dies no fallava.
No falla res, cap dia. Estan encarregant de nosaltres.
Què?
Estan encarregant de nosaltres. Espera, és que farem?
Us han fet prova especial o no? Us han fet prova especial?
No, la màquina no.
Ah,
no he pogut parlar amb ella.
La màquina no té interfície social.
M'imagino que en anglès, no?
Te l'ha portat preparada en castellà o en anglès?
La portava en anglès. Preparada està en anglès.
L'estan posant en anglès.
En català estaria bé.
O sigui, en cas que no funcionés la pantalla, us importaria fer la presentació només mirant aquí o ho veieu difícil?
Sí,
jo crec que està...
Si esperem una mica més a veure si ho arreglem.
Esperem a les 12.
Avui està fallant.
No, però encara que falli la pantalla, mentre tinguem el feedback aquí darrere, literalment la farà ell, jo crec que com m'ho digui, o no, si vols posar tu, no sé.
he vist el...
Hi ha un...
He vist el mando, o sigui... Per fer clic.
Té làser també, eh?
Sí? Ah, sí, és veritat. Aquí, no? No, no funciona. Ah, si l'enciendo...
Derecha, o què?
Sí, perquè allà a l'oficina tenim una tele i el làser no es veu, però aquí sí.
Escolta, pues, tirem sense pantalla aquestes.
Tirem sense pantalla.
Quan no hi ha conya, no? Ara buscant informàtics aquí a la Politècnica.
Hi ha molta més gent que està fora o és aproximadament això? Clar.
Perquè està pagat. Perquè està pagat.
No m'ho crec.
Necessiteu els altres?
No.
Si us necessiteu, aquí darrere hi ha un document.
És bo de saber.
Vale.
Ens l'han fet a peu, assegut...
No han fet a peu, no com vulgueu, o sigui...
Vale. La porteu en un USB? On està el...
Aquests sustos informàtics, per favor, aquests sustos mai més,
Encendre la pantalla.
Encendre la pantalla? A veure, això no...
Encendre i apagar.
Sí.
Fas tu presentació inicial o...? És igual, eh?
No, fes tu, home.
Faig
no, per fer jo... Hola. Jo mateix com a manera. Però... Passa que no sé si...
Sí, sí que funciona, no?
Hola?
Sí, ostres.
Pues fem... Canvies tu amb el clic i jo estic aquí i qualsevol cosa m'ho dius.
Canvia? No. Aquí. On està el PC?
Aquí. A veure, fes clic.
Sí.
Pues.
Well, bon dia. Good morning. Here we are, Paul and Manel. Hi. We came from Brightside. It's a Dutch company that recently opened a security laboratory in Barcelona, concretely in Sant Cugat. Well, we are here to perform some introductory presentation about side channel analysis. This is the agenda. So what to expect from the presentation? Of course, not become experts in side channels. It's not possible today, okay? But we will perform an overview of the state of art of different side channel techniques that are performed nowadays, and we usually perform in Brightside. So, well, does anyone knows what's side channel analysis? Just asking, no. Okay, side channel analysis try to recover information from non-direct information that can be obtained by observing something. Okay, in this case, it's just an example. We can know the activity that these guys were doing during summer just by observing the tan lines. For instance, this guy was doing water skiing, mountain biking, rollerblading, tennis. Well, okay. That one which is completely pale, it was expend all the summer programming. So, and the last one is scuba diving. Okay, another example of side channel analysis is the truth machine. We can know if someone is lying or not by monitoring the heart activity, or, for instance, directly taking a look at the pin pad, or observing, for instance, the pattern followed by the user. We can extract the pin number. Okay. So in the embedded world or the electronic world, it's a kind of analysis that takes advantage of intentional information leaked because it's physical implementation and architecture. And information that we can measure in some manner. Okay, the main leaked sources are timing consuming by the operations, the power consumption, or the electromagnetic field of the electronic devices. can be applied to the DES, AES, well, all cryptographic algorithms. Also in CPU operations, like XOR, copies, memory reads, whatever. And these are the main attacks. I want to remark that are the main, because there's a wide range of attacks existing nowadays. So this is more or less the basis of all the kind of, all the type of attacks that exist. Timing analysis, as I said, simple power analysis, which is basically a visual inspection technique to extract information from the power traces. Differential power analysis that also implies a statistical analysis. The same for the electromagnetic leakage source, okay, with the SIMA and DIMA. Correlation power with power and electromagnetic traces analysis, and template attacks. So, the aim for the attacker or the adversary is try to recover secret information from a leaking implementation. With, as I said, simple analysis, statistical analysis. And it's based on a divide and conquer strategy to, let's say, divide the problem. Okay, if we are trying to recover a 64-bit key, we will need to try this big number of tries to perform a brute force. But taking into account that devices are leaking information while they are operating, we can divide this problem in, for instance, analyze from 8 bits to 8 bits. The candidates then are reduced to 256, which is feasible. And that's, well, this is what I say, the attack takes a small part of the implementation and computes all the possible outputs for all the inputs. The example, the simplest example is some number, which is XOR with a key. So we can perform guesses of each byte, and together with some leakage source, extract information. To do that, we use distinguishers and some leakage model that I will explain later. Okay? And after that, the attacker could be able to recover symmetric, asymmetric keys, sensitive data, or even information of the flow of the implementation execution, etc. So, well, this is a simple example of a timing attack on the pin. We know that, well, we usually use the pin authentication to buy stuff. So this is a very bad implementation, okay, because it's doing the comparison digit by digit. And in case, and in case the digit is wrong, before check all the digits of the pin, it's sending a pin false message and increasing the counter. And in case the digits are right, it's continuing comparing. So there's here, depending on the digit that we are putting wrong or right, the pin comparison will take more or less time. So the thing is, okay, but we usually don't only have 3 tries, no, to check the pin. So what happens is if we perform if we cut the power supply, we can, with this technique, we can avoid the last part of the implementation, which is the pin try counter increase, and doing that and analyzing the timing that spends in each digit comparison, we can perform a brute force and break a pin. Sorry. Well, this is the basis of the power consumption analysis, which is based on all the embedded devices are built in CMOS technology, which consumes power when some in the state changes. Sorry. So here is the most simple example with a MOS inverter gate. Okay, when the input change from 1 to 0, we see the output change from 0 to 1. Current is flowing from VCC to ground, and we have this peak of consumption. And for instance, on the other hand, when change from 0 to 1, the output change from 1 to 0, and the capacitor, the load capacitor is discharged, and we can observe this other power consumption. What does it mean? This means that the power consumption depends on the data that the circuit is handling, and also on the pattern of switching transistors is performed. This allows an attacker to, by monitoring the power consumption, observe regular patterns on the power traces regarding some operations like cryptographic operations, memory reads, or whatever, and try to exploit this information to get secret data, mainly secret data. So how to measure the power consumption is as simple as place a resistor between the GND, the ground pin of the smart card, in this case, or some other device, and the ground of the circuit, and measure with an oscilloscope the traces. Nowadays, there are more sophisticated circuits and to perform this measurement, okay, with amplification stages and, well, circuitry. But this works, so it can be used perfectly to break some secure implementation. So examples of power consumption. Here we can see the typical power profile of a RSA implementation. Here the same for the AES. For instance, as during the AES are computed 10 rounds, which are doing more or less always the same, well, more or less always the same, with different data. But as I explained it, as the transistors are always performing the same kind of switching, we can observe the same kind of patterns and identify, for instance, 9 bumps regarding the 10 rounds of the AES. The last round, it's not computing the mixed columns operation, and it's missing in, sorry. So this pattern is missing here. Probably this is the mixed column power pattern, and here we can see that it starts, but it's not computed. These are some examples. And these are typical power profiles that we can see in fact in the real world. Okay, so the other leakage source is the electromagnetic emanation of the devices. It's a consequence of the current flowing. It's also a consequence from the current flow in the device. The current provokes electric fields, magnetic fields, and this electromagnetic radiation can be measured externally and, well, obtain the same kind of information done in power analysis. Or in fact, we can improve the analysis performed with power. So how to measure the EM signal? This is one of the setups that we have in Brightside. This is just a coil, It's a two-turn coil, and it's used to measure the electromagnetic of this chip, which is a smart card chip. We use all this setup, which is with a XYZ stage to perform surface scanning, but well, this is how we measure the electromagnetic emanations. So which are their characteristics? The measurements are done locally. If we here we can see that we are measuring only the electromagnetic emanations of a portion of the chip. That can be, for instance, the coprocessor or some memory or the CPU. And this sometimes leads in better signal quality than power signal, because in power signal we are capturing the power of the whole chip. And with EMA we can focus the analysis only on some interesting part of it. We need equipment to capture in the signals with a high bandwidth, above 1 gigahertz, and it's susceptible to external noise sources like radio, light, mobile phones, because we can capture all these interferences with the EM coil itself. So compared with power analysis is easy to measure. We can use low frequency measurements, and it's less susceptible for environmental noise. But on the other hand, with EM analysis, as I said, we can focus the attack on a concrete region of the IC, and thus bypass some countermeasures like random amplitude noise. If the chip has, for instance, some unit which is in charge only to introduce noise in the power signal, we can bypass this countermeasure with EM analysis. And also we can use the same to reverse engineering the AC. If we analyze the amount of leakage in each region and while it's computing different kind of operations, for instance, cryptographic operations or accesses to memory or whatever, we can use it to perform reverse engineering and extract information about the layout of the IC. These are typical power consumption and electromagnetic signals. For instance, this signal corresponds to a DES operation. If we are patient, we can count here the 16 rounds. And, well, as you can see, in the EM signal, it's not possible to observe the same. So normally, an attacker needs to use both leakage sources to conduct an analysis. But well, this is how the traces look like. Well, this is some picture of our equipment. We use Faraday cages to insulate the setup from external interferences. And here we can see this box is to capture the power consumption, and here it's the coil to capture the electromagnetic emanations. And this is some screenshot of our software. We use cameras and to positioning the coil, doesn't matter. So I mentioned simple power analysis, differential power analysis, or statistical power analysis. If we compare both analyses, the simple power analysis, its secrets are derived directly from traces, mainly using visual inspection. In DPA, it's necessary to perform some statistical things, which is known as distinguisher. In this case, it's the difference of means. Simple power analysis uses a small number of traces, and in DPA we need large number of traces, typically above 1 million traces in the current security evaluations. in this case, works with a leakage model. It can be single or multiply bit, Hamming weight, Hamming distance. And well, in simple analysis, we measure the duration of an operation and the power consumption, and in DPA only the power consumed. Okay, so this is another example of a timing attack, but based on simple power analysis. We have some implementation, okay, that it's making some decision it's executing two processes based on a decision. The first one takes 10 milliseconds and the second one takes 20 milliseconds. If we think, for instance, that this decision is based on a secret that we want to extract, by analyzing this timing, we can obtain some sensitive data. Okay, so this is the example to explain the second one, which is a timing attack on an RSA exponentiation. Most of you probably know how it works, the RSA, but I will perform some summary. The RSA has a key pair, which is one is the public key, the other one is the secret key, D. To perform encryption, performs the following: is a message to the power of E modulus N, and for decryption or signature, performs C to the power of D modulus N. So the most basic RSI implementation is the binary method, or also known as square and multiply. In fact, all implementations are based on the same kind of operations, squares and multiplies. And it's used to perform, well, during this operation that is handling the private key, we can target it and try to recover the key. So the algorithm works as follows. First of all, the message that we want to recover is initialized to 1, and for each k bit of D, from most significant down to less significant, the algorithm computes m to the power of 2 as square, and if the key bit is 1, then performs a multiplication, m multiplied by c. And if it's 0, then do nothing. Here we have this decision. We are performing two processes based on the value of each bit of the secret key. So if we analyze a power trace, we can observe the red marked bumps, and we can also observe that the durations are different. So green ones are greater than the red ones. So taking into account how the algorithm is working, we can guess that the key is, if it's performed a square and multiply operation, it's a 1. If it's performed only a square, not followed by a multiply, it's a 0, and so on. So just recording a single trace of doing the RSA computation, we can break 2048 RSA. Okay. Well, differential power analysis, as I said, involves statistical analysis and requires a large number of traces. It's based on the same principle. Devices are consuming more or less power depending on the data processed. So during the bit tracing DPA, the goal is to check if one bit value leaks. So the attacker needs to measure a large number of traces and split the set of traces into subsets. The ones that the target bit was a 0 on the one hand, and on the other hand, the traces that handles a 1, and perform the average trace of those traces and the average trace. This is performed for each known or guessed value. Okay, if we are trying to discover some leakage in the power traces with the input data, for instance, the input data is known, and this technique can be applied to locate the instant where the input message is being processed. Or if we want to discover some secret, like the key, we can focus the analysis in some operation and perform guesses of all possible values that this key can have. When these subsets are subtracted, we will be able to observe correlation peaks. So how it works? For instance, if the guessed value it's not correct, we will be grouping those traces based on a wrong assumption, and those traces, and where those traces have been manipulated, zeros and ones indistinctly. So the average of this subset and the average of this subset will be similar, and the different trace will tend to 0. But what happens if the guessed value is correct? We will performing the right grouping. The zeros consumes less power than ones, and when both average traces are subtracted, we will identify a correlation peak, a peak that it's usually known as correlation peak. So, well, I want to say that, or remark that this peak theoretically will only appear when the correct guess is used, but in fact it's appearing in more cases that we will see later. Okay. So, for instance, for a known attack, we will be able to see different correlation peaks as these bits have been manipulated. For instance, focusing this example on the DES, the DES, well, this is the scheme of the DES, is performing 16 rounds that we will be able to identify, but performing an SPA. And we will focus the attack. For instance, we can focus the attack, for instance, here, after this operation. The input is known. We can calculate the input till this point. And at this point, we can perform guesses of the key and perform the DPA. We can also focus the attack here at the output of the S box, or for instance, at the output of this XOR with the left part with the output of this function. There are more points because we can use the Hamming distance between the output of the XOR and the input, the output of the S box and the input, the Hamming distance between these points, or between these points too. This is just to explain that there are a lot of points that we can target during a DES, and in other algorithms is the same. And probably during the implementation, you can be protecting this part, but not this part, or not this part. So evaluators shall be careful when they implement cryptographic algorithms. So the process is the same that I explained. the attacker needs to make hypotheses of the possible values of the key and compute operations with the real key and also with the guess, and record a power trace. The same for a net guess, the same. And after the analysis, this is this is a picture of a real output. In this case, the correct key was the candidate 24, which is giving the maximum amplitude of this peak, and other sub-candidates are giving, well, less amplitude. So this is the distinguisher to identify if the correlation, if the guesses were correct or not. Another distinguisher is the correlation power analysis. It's based on the same principle than the DPA, but is a more sophisticated one. The CPA targets the correlation between data and power. As I say, it's more powerful than DPA because it's able to avoid ghost peaks. For instance, here we could obtain two values with similar, with the same, for instance, the same correlation or the same amplitude of the peak, and this will lead to confusions during the analysis because you will not, well, you can be confused between two similar peaks. So the CPA, the aim is to avoid this kind of problems. Uses Hamming-Wave models, assuming that power dissipation is proportional to the amount of non-zero values on the processing data, or Hamming distance. That uses changing logic values from the previous value that, for instance, some register have to determine the power dissipation. And the distinguisher, in case of DPA, is the difference of means. Here, it's this formula that gives a correlation coefficient. So how to compute the dependency? We analyze the power traces. In this case, for Hamming-Wave, the Hamming-Wave it's 6. In this case, it's 5. In this case, it's 3. For the different points that these bytes were manipulated, and well, the same for the Hamming-Wave distance. Sorry. So, how we use the correlation results? The peaks in the correlation traces show if and when the data was used by the device. For instance, if we perform correlation analysis with the input data and also with the output data, and we find peaks here and peaks here, we can ensure that the cryptographic operation, for instance, it's performed between both peaks. If we cannot find any peak, this is because 3 reasons. Data is not used during the investigate time frame. Okay, maybe the system is leaking, but we are analyzing this part and the messages are handled here. The data is used in a modified form, sorry. For instance, by applying some blending or masking countermeasure, or the amount of noise is too high. So again, it's a summary of what side channel analysis. The attacker forces the device to compute some operation with the keys that wants to obtain, at the same time predict these hypothetical values, capture the power or the EM traces, and compute some leaking model based on Hamming-Wave distance or Hamming-Wave or Hamming distance, and finally use some distinguisher to find if this leakage model matches with the capture traces. Com anem de temps? Sí? Template. Well, template attacks is quite new attacks that are also based on analyze the power or EM traces and its leakage, but it's matching the build templates with the real consuming or with the real leakage with a probability with probability match. Sorry. Can retrieve information from any operation with sensitive data. Till now, DPA or CPA are based on performed guesses of the output of some operation. But in this case, we don't need to analyze a concrete operation because we can use template attacks to break, for instance, a kilo adding, for instance, from memory to CPU, or some string copy, or some write or read operation, or even during cryptographic operations. Well, template attack consists of two phases. The first one is the training phase. The attacker uses a training device, which is similar to the one that want to attack, and use known data and acquired traces to, on the one hand, knows the behavior of the device, and during this phase builds the template for each class. Each class is, for instance, all the possible values that 1 byte of the key can have. And during the challenge phase, captures some signals from the target device and try to match if these templates are similar to the information acquired with the device by using some probability distribution of the related noise to this information, these traces. In the real world, templates are generated with an open device. An attack is applied to some target. Can be used the hardware, the Hamming weight model or the exact value of each byte. During the characterization phase, I mean, these templates are applied. Power or EM profiles are characterized with a mean vector and a covariance matrix. And as I said, evaluates the probability function of how the noise distribution observed corresponds to the one of each class obtained during the building phase. In this case, we have a template match, and we will able to recover secret information. So the highest probability is expected to be in where the correct guess is used. So we have the device under control. We know, for instance, that zeros consumes this amount of power and ones that amount of power, but in fact, in the attacked device, it's not real, because we are considering bytes, not bits. So we will have classes for all the bytes. We can use Hamming weight or the exact value. In case of using the Hamming weight, we will have 9 classes. And for the exact value, 256 classes. And the challenge traces captured with the target device will compare to no, sorry, the challenge traces, yeah, are the templates are compared to the traces captured on the target device. One of the most important parts is the point selection, because we cannot apply templates on a very wide trace, because it's computationally it's not feasible. So we need to select those points where the most promising leakage can be obtained. One of the techniques used is, or the statistical analysis used, is the SOST, sum of the squared pairwise T difference, which is considering the mean of the signals to select all these points. We need to think that the covariance matrix that we will build during the training phase will grow quadratically with the size of these points. So we want to apply the templates only in a small part of the trace, because if not, we will not be computationally able to break some key. So, well, the classes are represented by these templates is the vectors of means and the covariance matrix. For each class, we will have this. And the matching is done with this big formula. Okay. This is the challenge trace. Here we have the template. The E is the input data and the key. One important thing to remark is that the result is a probability. So at the end, we will have a probability on how those templates matches with the challenge trace. So, well, it's only a probability. So where to apply the template attacks? Or which is his application? Well, as I said, we will need open samples for the training building phase. Can be applied to single or n traces. This because it's so powerful, because if we have a similar device, we build the templates, we can break some other device only with one capturing of a power or EM trace that can be obtained, for instance, by some spy antenna or some circuit in some real device. Can be applied, as I said, to the same device, to other device, or even with similar devices that are not exactly the same. For instance, templates works between chips of the same family. That are different, but are chips of the same family. One of the powerful things is that the training phase can be performed in a different command or process. For instance, let's imagine that the string copy function used to copy or to move the secret key from the CPU to the coprocessor, to the DES coprocessor. It's the same function used to copy the APDU buffer. The APDU buffer is the APDU is the message that we are sending to a smart card. The user will have full control, that has full control of the APDU buffer without an open sample, will be able to build these templates and apply the templates to his own, for instance, the electronic ID card. And well, template attacks on large number of classes will become computationally infeasible. We think that we are attacking only 1 byte. We have 256 possible combinations. If we need 1,000 traces to build each template, we will need to capture this amount of traces. So this is quite feasible. But if we try to apply the same for 2 bytes, the amount of traces needed is quite high, and will consume a lot of time to do that. So, well, and so on. Let's imagine that in the real world, with 1,000 traces, probably you will break nothing. And normally are needed 1 million traces in that order. So, well, how to protect this implementation against side-channel attack? We first need to think what makes side-channel attacks possible. We have a dependency between the power and electromagnetic signal with the processed data. And if we have this dependency, the first thing that we want to perform is or hide this dependency or perform some masking blinding to modify the processed data and well, not allow to perform guesses. Okay, because if we modify this data internally, we usually take advantage of that. We know the input or the output, for instance, and we can guess some parameter of an internal operation. If we mask, for instance, the input or the input, we will not have any information to work with. So, for instance, to hide this dependency on the power or electromagnetic signals, we can interleave dummy operations between in the code. We can do shuffling. We can increase the noise with some parallel activity. We can apply time jitter to synchronize between the different executions the time where the same operations are being performed, or apply some amplitude noise. And if we want to mask or blind this data, well, some easy thing that can be done is to XOR on each computation the message that we know with some random number that obviously we can not know. Perform some modular operations for the case of the RSA, for instance, to blind the data, or perform a combination of all the countermeasures. However, some of these countermeasures can be counteracted and exploit. Well, it will be more difficult, but at the end, we will be able to break the device, likely. So, for instance, for hiding countermeasures, normally the only thing that we need to perform is to capture more traces. Okay, for instance, to compensate the noise, or to have enough well-aligned traces to avoid dummy operations or time jitter, for instance. For this type of masking, there are other types of attacks, like high-order DPA, that will correlate the known message, the power trace, in this point where the mask is applied, and here where the mask is deshecha. Well, where the unmasking operation is performed. We will use 2 points of the power trace to apply the same DPA or CPA techniques that I explained before. We can use also frequency domain to avoid some of the countermeasures like noise, time jitters, or for instance, to break blinding or masking operations on asymmetric algorithms. There are some horizontal analyses based on the same SPA and DPA, but only using the patterns observed in the single trace. This is, well, I don't have enough time to explain that. So, well, conclusion, what have we learned? Sidechain analysis is a family of implementation attacks. Exploits data dependencies in time, power, or electromagnetic channels. Sidechain analysis can target public and secret key crypto algorithms. Correlation analysis is the most simply and efficient measure to obtain data leaked. Analyzing how much leakage exists, if it is exploitable or not. Sometimes there is some leakage, but you are not able to identify real and fake leakage and distinguish between them, and at the end you are not able to break some key, for instance. Can be used also to know the intervals of during the process where the data is manipulated, and what can be used to perform key search. EM channel is an improvement of the power analysis. We can target local emanations on chip surface, as I said, by placing the EM coil and focus the measurement on one component of the IC, and hence obtain cleaner measurements. And what? Template attacks, which is a type of attack that models the leakage, needs open devices, and provides better results. Well, side channels can be applied to contactless interfaces too. Well, I explained some countermeasures for side channel. Well, for instance, can be applied to terminals. Well, any embedded device is vulnerable to this kind of attacks. So one step further. Well, as a laboratory, we need to be on the state of art, because side channel techniques and side channel attacks are varying constantly. For instance, now some template attacks using deep learning techniques are appearing, and laboratories like us, we need to take it into account. Exists the white box crypto, which is the same kind of side channel analysis, but instead of using power and of physical measurements, are applied to software traces, for instance, recording all the registers the registers used during a cryptographic operation. Exists also the perturbation attacks, focus on inject faults during the behavior of some device and provoke bypassing, for instance, some operation. In the PIN example, we will be able to bypass the PIN check with introducing some fault. Now, well, Paul will explain you some details of BrightSide. Thank you.
Well, sorry for the spam. Well, we want to talk to you a little bit about BrightSide. BrightSide right now is the first security lab in the world. Well, because it's a bigger one. We have 3 sites right now. The main one is in the Netherlands, in Delft. And then we have one in Barcelona and one in China. We work for many different certification bodies, but most especially with common criteria and EMV, MasterCard, Visa. And nowadays we are also starting to invest some effort on mobile payments. You may have already heard about HCE and TE. We have a lot of years of experience, especially in Delft. The company in Barcelona, it's pretty new, so. And well, if you have any question about the company or about the presentation, we'll be here to just answer it. No? Well, since we have just opened the company in Barcelona, we are looking for new engineers. So if any of you are interested, please just let us know. We have career positions for side channel, for analysis, also for source code review, also for robots engineering, all this kind of stuff. Just send an email to that address, or just come here and talk to us, and we will let you know. Okay, thank you.
Thanks for coming. I may be interested in joining. We'll proceed with our schedule and follow with our talks this afternoon at 4. So make sure to be here. And I really hope that you enjoyed everything of this, just as we did. Thanks.
Sí, hòstia, massa corrents i poc temps per preparar res.
Bueno, però almenys està bé. Hem acabat com tocava. Hem acabat. No? Tot correcte. Ara anem a dinar al Siló. Nuri, vine un moment, sisplau. Sabeu on estàs esperant al Siló? Heu aparcat?
Hem aparcat davant de l'estadi del Girona.